Hello and welcome to the virtual implementation workshop on time-of-flight and quadrupole time-of-flight mass spectrometry for identification, screening, and confirmation in forensic toxicology and chemistry. First up, we will hear from Dr. Alex Krotulski with the Center for Forensic Science Research and Education. Without further delay, here is Alex.
Hello, everyone, and welcome to this HRMS RTI webinar. I'm excited to kick things off here with some theory into data-dependent acquisition and data-independent acquisition. And I should caveat this before I start with saying that most of what I will discuss today really applies to both TOF and QTOF. There are other high-resolution mass spectrometry platforms, things like Orbitrap, that I will not cover today. Certainly that information is of interest, but that will have to come at a different time. So again, today I'm going to start us off with some theory. So by way of introduction, welcome you all again to this webinar. My name is Alex Krotulski. I am an associate director at a organization called the Center for Forensic Science Research and Education, and I manage our NPS Discovery program. I also hold faculty appointment at Thomas Jefferson University. Hopefully many of you are familiar with our program. If you're not, you can visit our website and can learn more about our organization. We have quite an interesting history with the use of HRMS platforms. We've got about a decade now of experience using various vendor platforms and software. We've kind of seen the evolution of acquiring new instruments, having to validate those new instruments, trying to mirror instruments together. So this is not something new for myself or us, and something that we're quite passionate about. We use our HRMS platforms quite regularly. And yes, here we are. So again, I work for the CFSRE. We are a nonprofit research and educational facility performing both, obviously, research and education per our name, but we also do surveillance work and casework. So while I am going to mostly focus on theory today, you're going to hear a little bit later on from folks in various labs across the country who are using QTOFs mostly for casework, and you'll hear about some of that DUID or postmortem casework and their workflows. We use our QTOFs, again, for slightly different scenarios. We do use them in casework, performing both postmortem casework and, to a lesser extent, impaired driving casework. But we more heavily use our instruments for our surveillance work that really benefits a number of public health projects that we have and really public health as a whole. So again, some of you may be familiar with that work. Here's a picture of our laboratory. Very nice. It will look new soon. We are moving in a few months. And you can see on the top right there, we've got a number of QTOF platforms. We have a Waters QTOF and two SciEx QTOFs. All right, so let's jump into this theory. So first, we've got to talk about targeted versus non-targeted and really defining them. So when you go to the dictionary, you'll find that the definition of targeted is directed at a particular group or activity, and I've added analyte in there because that's really our approach here as we talk about mass spectrometry and the work that we do in forensic laboratories. And then non-targeted is not directed at a particular group or activity, or again, analyte. So when we think about targeted versus non-targeted assays, there's certainly benefits to both, and there's reasons why you would use both. And sometimes there's reasons that you could use either, and one is not necessarily better than the other. It's just making sure you've got an assay that you're using and that it's validated and that it works well. So our targeted assays are going to be more specific assays, direct assays, assays that are intended to detect certain things. They're going to be focused on maybe a group of drugs or a class of drugs, and they're going to be a little bit more straightforward. So when we talk about our targeted assays, a lot of times what we think about right off the bat is our LC triple quad MS targeted assays, where you've got an MRM method set an MRM method set up, you've got the set points for your method in there, for your precursor ions and your product ions, and you're targeting those drugs. You may be looking for 5 drugs in the same class, or maybe it's an opioids panel or a fentanyl analogs panel, whatever it may be. The sort of complete opposite of that is our non-targeted assays. So they're going to be more non-specific. They're generally going to be more comprehensive. A lot of times when I describe our non-targeted assays, I call them sort of broad-based screening assays. And inherently, they're going to be more complex and complicated. And the reason for that is you've got a non-targeted assay. We're going to get into this more, but you're generally acquiring more data. There's much more to comb through. You're not only maybe acquiring 10 transitions for a few drugs. You're actually acquiring much more data. And so, how does this now relate to forensic practice? Certainly. Again, there's reasons why targeted and non-targeted assays can be used. I think when we start to think about the theory of non-targeted assays, we often start to think, well, that sounds like the opposite of what we want to do in the forensic world, right? In the forensic world, we want to know exactly what we're looking at. We want to make sure we've got high accuracy, high specificity. But the reality is that you can have those with the non-targeted assay. So it doesn't necessarily mean that we can't use non-targeted assays in the forensic world. And to be honest, I always say nowadays that really targeted and non-targeted assays can be used to complement each other. And then this gets into sort of this idea of, well, where do we use the terms targeted and non-targeted? And we use them across all of our different pieces of the workflow. So when you think about your workflow from beginning to end, you get a sample in, you prepare that sample. The preparation you do on that sample is going to be either targeted or non-targeted. If you're using just a basic liquid-liquid extraction, you are targeting drugs that will become unionized in the basic form, right? If you're using an acidic liquid-liquid extraction, you're going to be missing all of those basic components. If you're using a solid phase extraction, there may be certain things that you're targeting over others. So there are a lot of sort of scenarios there where you're going to be either very targeted or somewhat targeted or maybe even non-targeted as it relates to your sample preparation. Then we've got our instrumental analysis, and I'm going to come back to that because that's really what we're focused on today. And lastly is data processing. So I would argue that almost all assays in the forensic world are targeted assays. And the reason I say that is because of the data processing. So while we may have non-targeted sample preparation and non-targeted analysis, on the instrument side, almost everyone in the forensic world is using a targeted data processing strategy. And the reason for that is because non-targeted data processing strategies are very complex. And if we're trying to report something, if we're trying to confirm it, we'll already know what it looks like. We've already got it in our library database. And again, that goes down that targeted route. So, but again, moving forward today, we're going to talk more about instrumental analysis and specifically about TOF and QTOF as it relates here. So during instrumental analysis, there's 2 pieces that can be targeted or non-targeted. The first piece is chromatography. And I'm just going to breeze over that and say that for chromatography, if you've got sort of a generic gradient on an LC or a generic temperature program, you can kind of consider that as kind of a non-targeted assay. But really, the mass spectrometer is where we get into sort of the nuts and bolts of what is a targeted or non-targeted assay. So that leads us right here. So what does this mean in terms of TOF and QTOF? Well, TOF methods in general are going to be non-targeted assays. And they're going to be like our GC-MS full scan assays. That's kind of the best comparison. So a TOF-MS only is going to do a TOF scan, right? There's going to be we don't have a quadrupole there. There's going to be no filtering of ions. So really, if you're scanning a range of say 50 to 500, that's really a non-targeted analysis across that range. You're not really specifically targeting anything in there. Whereas our QTOF assays are really the ones that can be used in both targeted and non-targeted fashions. And actually, they're used concurrently. You've got a non-targeted, potentially, you've got a non-targeted TOF-MS scan, and you can have a non-targeted or a targeted MS scan, and we'll talk about, or scans, and we'll talk about what that looks like. So here on the right is a picture of specifically of a QTOF. And really the pieces that we're going to focus on today that are most important are the quadrupole, the collision cell, and the TOF analyzer. Certainly, you've got an ion source and you've got ion source parameters that are important. However, most of what we do, the ion source parameters are set. They work really well. Mostly everything we deal with is fine in positive electrospray ionization. TOF analyzer is going to work its way. You're going to have the ions pushed down the flight path. They're going to eventually be detected by a detector. There's not many set points to change there. It's really going to come down to your quadrupole and your collision cell and how those are functioning. And I'm going to walk through some of those examples of how they function. So really, when we talk about the quadrupole in a QTOF, we talk about it in these sort of different ion filtering and fragmentation techniques. So there's a bunch of different ways that a QTOF can function. And just because you have a QTOF doesn't mean it can function in every way that I will mention today. Different vendors and different hardware systems, the actual instrument themselves, may or may not be able to do certain quadrupole filtering. Almost all QTOFs can do this first thing, which is sort of MS to the X, which would be your akin to like an MRMHR analysis, an MS to the 2 analysis, where your quadrupole filters one ion, it fragments that one ion in the collision cell, and then those fragments go to the TOF analyzer. Pretty much every QTOF can do that. I'd probably be pretty confident to say they all can. It's really these next few and how the hardware and the software communicate for the vendor that may or may not be possible on your instrument. Again, with this MS to the X, so it's MS to the 2, generally. When we talk about Orbitrap and traps, you can get into other scenarios, but for this, it's really more of an MS to the 2 analysis. You're passing just one mass at a time through your quadrupole. The next option is that you can pass all masses to the quadrupole, pretty much turn the quadrupole off and have it function as an ion guide. And that would be more akin to analyses like MS all or MS to the E. So if you have a Waters platform, you may have heard of MS to the E. And you can see the graphic there. Essentially what happens is your quadrupole is not filtering any ions. It's allowing whatever's gotten through your source and all of your lenses and things to go through the quadrupole, make it to the collision cell. There will be different things happening in the collision cell. Again, the collision cells function a little bit differently, and I'll mention that at the end of the slide. But you'll get fragmentation, and those fragments will go to the TOF analyzer. And then the third option is, well, you can use your quadrupole to filter a group of masses. And that technique can be called MS all. It's a technique that SciEx uses and calls swath, if you've ever heard of swath acquisition. You can see on the right there, you're not getting all ions passing through the quadrupole. So you've got a select number of ions, precursor ions passing through your quadrupole, some being filtered out, going to the collision cell, being fragmented, and those fragments going to your TOF analyzer. So again, back to the collision cell. Collision cells can function in different ways. I don't want to go over this too much, but as you can imagine, different voltages can be applied there. You can have set voltages, low and high energies. You can have a scanning or a range of voltages. SciEx calls that a collision energy spread, where it actually uses collision energies from 15 to 50 and cycles through those. So there's different ways those collision cells can operate. But the sort of take-home message here as we start to go through more of this is that your acquisition mode is absolutely going to dictate the data that you produce and the possible outcomes of that data. So this is something that's always challenging because when a laboratory gets a QTOF for the first time, they often very early on have to make a decision about what acquisition mode they're going to use. Are they going to do a targeted or a non-targeted method? They're going to go the non-targeted route. What option are they going to use? And sometimes the vendor will provide options for that, but it's challenging because you haven't seen the data yet, right? You're not going to know if it meets your need until you started acquiring a bunch of that data. So I always recommend kind of evaluating both or evaluating multiple acquisition modes to be able to figure out what best suits your lab. And again, you're going to hear about more of that later today. So getting more into the acquisition modes in terms of data dependent versus data independent acquisition. So data-dependent acquisition is a targeted acquisition mode. Some platform or some vendors, including SciEx, call that information-dependent acquisition. It's going to be a specific, sort of non-inclusive, and it will happen on a cycling basis. So this is kind of the way that I always explain data-dependent acquisition. It is your MSMS data. That means your fragment data. So your every QTOF is going to do, well, most QTOFs, the way you have them set up, are going to do two mass scans. The first is going to be a TOF-MS scan. The second is going to be that fragment scan, which is called the MSMS scan. That's important to understand because when we look at data, and I don't think I get much into that today, but others probably will. When you look at data, you actually acquire two mass spectra during a QTOF analysis. I think some people kind of maybe don't see that or forget that, but you're acquiring two mass spectra and evaluating two different mass spectra. So it's important to understand that those two scans exist. So this second scan, this fragment scan, is the MS acquisition. And when you've got a data-dependent acquisition, it's going to be dependent on the sample. So something in the sample is going to dictate whether or not, or potentially in the method, is going to dictate whether or not certain fragment ions are acquired. And I always boil that down to math and saying, if X, then Y. So good examples of data-dependent acquisition modes are if you've got a mass list, you program into the software, these are the masses I want you to isolate in the quadrupole, and I want fragment data for those ions. That is a data-dependent acquisition mode. There are other data-dependent acquisition modes that will isolate things in the QTOF based on retention time, based on intensity. SciEx's platform has an option where you can, during a given cycle, you can fragment the 16 most, or pick a number, most intense candidates. That's their sort of IDA method. So again, this is going to be a data-dependent acquisition mode. Something is going to dictate why you get fragments occurring. And one of the ways to sort of explain this, because I think a lot of people understand MRM, this is really an MRM-HR sort of type of scenario. You can run, like, if you're doing an MRM-HR quantitative analysis, that is a data-dependent acquisition. You've got your ions, your transitions in there, and that's what you're acquiring. So that's data-dependent acquisition. If we flip over to non-targeted acquisition, now you get data-independent acquisition. These are going to be your generic independent acquisition modes. Again, still cycling. Again, still acquiring two spectra, your TOF-MS spectra and your MSMS spectra. And then these are the different options. I've already talked about MS to the E and MSMS all. Those are possible with waters and adjuvant systems. And then this MSMS all swath acquisition is possible with SciEx systems. There certainly are other options out there as well. These are just some examples that I've listed. And obviously, this is not an all-inclusive list of all the vendors that exist out there. So I'm going to go through and kind of show some more graphics so you can see how some of this works. So with our acquisition modes, again, it's all dictated by what's happening in the quadrupole. Is the quadrupole acting as an ion guide, or is the quadrupole acting as a mass filter? And then is the collision cell on or off? During a TOF-MS scan, to get your precursor ion, your quadrupole acts as an ion guide, your collision cell is off, so you get your precursor ions to float through and make it to the TOF analyzer in their intact form, in their precursor ion form, and that's how you get your accurate mass. And that is again, precursor ion, your intact molecule. When you turn your collision cell on, then that's when you're getting your fragments. So, and again, the collision cell can function in different ways. One thing I like to do is kind of compare this to some of the other analysis or acquisition modes that we use across other platforms, because then it makes it, I think, a little bit more obvious as to the examples of each. So when we talk about targeted or data-dependent acquisition, we talked about IDA. That's going to be similar again to your triple quad and in filtering precursor ions, fragmenting those precursor ions, and then individually and then getting those fragments. When we talk about non-targeted or data-independent acquisitions, we're talking about MS to the E or MS all. Those are going to be more like a GCMS full scan method, right? That's a full, truly non-targeted method, generally, depending on the different set points. And again, these are going to be more like our GCMS methods. This is an interesting graphic, and I'm sorry it's not as high of quality. This is the highest resolution that was in the paper. But this is a really good way of showing what this looks like in 3D. So we often sit in front of computers and they're two-dimensional, and the vendors have great software that shows us all the data in 2 dimensions. But the reality is that when this data is being acquired, there are 3 dimensions. You've got your dimension of time from chromatography. You've got your dimension of masses from the mass spectrometer, and then you've got your intensity. And then it even gets a little bit more complex within there because you've got precursor ions and their mass and their intensity and then the fragments of those. So it does almost become 4D-like, if you will, but not really. But this is what this looks like. So this is, again, along the x-axis here, you can see time. That's your chromatographic separation. Along the y-axis, we have intensity. And then you can see sort of this is a swath acquisition. So these are different pockets of ions that are being sequestered in the quadrupole and then fragmented together. And you can see that as you go through the different swath windows, as they call them, you actually get these peaks in different windows. And it's really cool. There's a lot of really cool things you can do with this. And I'm going to show some data in a little bit. But yeah, I think it's always important to remember that this is really happening in 3D, even though our brains don't necessarily think that way often. And then coming back to a 2-dimensional view. Again, this acquisition is happening on a cycling basis, and this is again just another way of kind of showing you that the TOF-MS scan is happening all throughout the cycle, all throughout the acquisition. It's happening generally across your mass range, depending on how your method is set up. And then an example here, at least for swath acquisition, is that you can get these sort of variable fragment ion acquisitions. So every method is going to be a little bit different depending on how it's set up. The cycle time for your instrument could be anywhere from 0.1 to 0.5 seconds. It has to be obviously faster than your chromatographic separation is, and your chromatographic separation is generally happening on the minute to sub-minute scale. So it really depends on how many, really for a swath method, it depends on how many windows you have and how quick your cycle time is. But again, it's happening extremely fast. In every cycle, you're acquiring that TOF-MS data. So every cycle, you're acquiring data for precursor ions. And then sort of throughout, you're acquiring different types of fragment ion spectra. And again, this is a different way of viewing this. This was the new paper that came out recently. And you can see just some different examples up here on the top left. You've got data-dependent acquisition. And you can see kind of what's happening in the quadrupole in terms of you've got all of these masses from what's eluting off of your chromatographic system, what's being sort of ionized in your source, get to a point where the quadrupole gets to filter those out. If it's a data-dependent acquisition mode, it's generally going to focus on just one ion or one mass. It's going to pass that mass, fragment it. You're going to get those fragments, and then you're going to get those fragments appearing in your mass spectrum. And again, this is an MS-MS spectrum, your fragment spectrum. The thing that would have happened before this is that TOF-MS scan, and you would get that precursor ion. And then again, down here is your data-independent acquisition, where you're filtering sort of a range of masses, but not all, a range of masses, filtering those together, fragmenting them, and then getting a fragment spectrum. So a couple of things to note here. This first graphic in these, this MS-MS isolation, down here with data-independent acquisition, this is just showing that this is happening on a cycling basis. Whereas up here with data-dependent acquisition, this is showing that this happens when something is triggered to be isolated. So it's not happening on a cycling basis. That's why one's data dependent, and the other one is data independent. The other thing I want to mention here is that you can see based on these MS spectra, these fragment spectra, you're probably thinking, well, why would I ever use data independent acquisition? That looks really messy. I don't want my fragment data of all my compounds in one spectrum. The one thing I always remind people is that there is chromatography associated with this. Our QTOF methods are 15-minute methods. We are separating, we're doing a lot of separation on the front end. So there's not much concern there as it relates to having this messy of spectra. Is it possible, and sometimes do we get two ions that elute from the LC at the same time and are within the same swath window? Yes, it can happen. Is it rare? Absolutely. Even though we are doing a data independent acquisition, our MS spectra do look a little bit more like this up here on the top. We don't have this much messiness going on. So to kind of just take a step back and sort of compare these two. So when we got data dependent acquisition, we're talking about high specificity. You've got certainty in your fragment to precursor correlations. If you are trying to do something like structural elucidation, and you want to have absolute certainty that a fragment came from a precursor ion because you need to use that fragment to elucidate the structure, and data-dependent acquisition is the way to go, right? I mean, that's where you're going to get your most high certainty because, again, based on that last slide I showed, you can have multiple things fragmenting, and you can get fragments from multiple precursor ions in your spectra for data-independent acquisition. But again, not as common. So again, high certainty there, data-dependent acquisition. Your isotopes are discernible generally through your accurate mass, and the reason for that is I didn't actually go into much of this when we talked about precursor ions, but when you think about your precursor ion data, you've got your monoisotopic mass, and then you can have you can see your M+2, M+1, M+2, and that's where we look at M+2. Is it chlorinated? Is it brominated? When you're isolating these ions in the quadrupole for fragmentation, you lose that M+2 when you're doing a data-dependent acquisition because you're only isolating generally the precursor or the monoisotopic mass. So that's why I say isotopes are discernible through the accurate mass itself. You may know it's brominated because the decimal place is 0.99 something. You're not actually going to see the bromine, M+2 for the bromine isotope. And then again, DDA is maybe more ideal for structural elucidation. Flipping all the way to the right for data independent acquisition is kind of the opposites, right? You're going to have lower specificity again, but remember you have chromatography, so you do still have pretty good specificity there. Isotope patterns are more obvious. So when you are passing a range of masses in the quadrupole, you actually pass the monoisotopic mass and the M+2, M+1, and the M+2 together, so you can actually see sometimes better that your fragments are brominated or chlorinated. And I'm going to show an example of that in a moment. Generally, data-independent acquisition modes are more for comprehensive screening. And then there's some interesting things you can do with extracted ion chromatograms you can't do with DDA methods. And again, I'll show that in a moment. And then sort of in the middle is what you can do with both. Again, both are perfectly valid ways to acquire data. One is not inherently better than the other. It really depends on what you're using the acquisition mode for and how you're setting up your method. If you hear someone say, oh, my data independent acquisition mode is terrible, it's got a lot of false positives or false negatives, that's not necessarily the fact that it's a data independent acquisition mode. That's all the other set points that go into it, right? How are samples being prepared? What are the set points of the DIA method? What are the data processing criteria? It's not the fact that it's DIA, so keep that in mind. Again, both can be employed, or both are employed successfully by many toxicology and chemistry forensic labs. You'll see or hear more people talk about that today. And then lastly, both have library search capabilities. However, they may just have to have a little bit different of set points. If you've heard things of like fit versus reverse fit library matching, there are just some different types of things that go into that. And I'm not going to spend too much time on library searching. Both can do library searching. There's just some caveats there. So let's look at some data examples because these are what I think are quite interesting. And again, when you get an instrument and you're tasked with figuring out, okay, well, do I go data independent or data dependent acquisition? This isn't what you see, right? So you really have to kind of talk to your colleagues, talk to the others in the field that have the same instrument maybe and have been using it for a while. Or you need to kind of embark on this endeavor. It's very much like a research endeavor and figure out which one you're going to use. So you're not going to get a QTOF in your lab and start using it the next day, right? There's a lot that may need to happen in that method development stage, and that method development stage could be several months, on top of then however long it takes to validate that assay. So yes, let's go through some of these examples. So your acquisition will absolutely have impacts on your chromatography, and this is what this is showing here. So I'm going to start with the left one. The left one is a data-dependent acquisition mode. This is an information-dependent acquisition where the precursor ion is being isolated based on its intensity. So is it one of the 16 most intense ions or candidates, as they call within a cycle? So on the left here, you can see this sort of back color here, this thing that looks like a chromatographic peak, that comes from your TOF-MS scan. And that looks, well, it's not the best, it's not smooth, obviously. That's what your sort of TOF-MS data will show you in extracted ion chromatogram. Then you can see here at this 4.95 minutes, you've got a spike. And that spike is because you've got that precursor ion that's been isolated in the quadrupole. It's fragmented, so you get this intensity there during that cycle, but then it's not isolated again, so you only get that one intensity. So if you try and overlay these chromatograms, you can see, well, you can tell that maybe this 4.9 minute spike came when the precursor ion was eluting from the LC system in general, but it's really not as correlatable as here on the right. So because and this is a data independent acquisition, over here you can see because we're acquiring ions on a cycling basis, we get these data points all throughout. We're not waiting for the software to say, target this ion, I want to see its fragments. So what you can do is you can actually overlay the chromatograms, and I can't tell you how many times we've done this in our lab. This is very helpful. We use data dependent acquisition. Spoiler alert, if you hadn't, if you don't already know that or hadn't figured that out, but this is extremely useful to us in saying, well, do these ions match up? Do I have higher certainty that this is really what I'm looking at? There will always be, with non-targeted acquisition mode, certain ions that appear here or there that are kind of weird, especially with post-mortem samples. You never really know what type of ions are going to be acquired. So this can be really helpful in, again, stacking and overlaying these extracted ion chromatograms. And again, this is just some additional examples of impacts of chromatography. So these are all data-dependent acquisitions, and you can see these sort of spikes. It's not as nice and neat looking as it is here with the DIA and overlapping the chromatograms. So again, this is what we do. Our method, we have data, we have listings in the software to extract out the extracted ion chromatogram for the precursor ion and its 5 most intense fragments. So we can do this. And again, we've used this on a number of occasions for help in figuring out if something really is what we're looking at. And again, this is another way of looking at it. Here on the top is your TOF-MS extracted ion chromatograms. On the bottom is your fragment ion, your MS-MS chromatogram, extracted ion chromatograms. The left is data-dependent acquisition. The right is data-independent acquisition. So again, if you're going to try and process data like MR-MHR, if you want to use this chromatography from your product ion, You can only do that through data independent acquisition. This chromatography over here on the left with data dependent acquisition, you can't use that for anything. So if you want to use it for ion ratios, if you want to use it for overlaying, if you want to use it for whatever, you really need to be acquiring that in a data independent fashion. Here's an example of data dependent versus data independent acquisition. So this is a weird example that we saw with MDMA and oral fluid. On the left, data dependent acquisition. You can see the fragment spectra is just a fragment spectra by itself. On the right, you can see we've now got this 221 ion that's eluting at the same time. It's fragmenting within the same window, and we get the data in here for that other ion. So this is kind of a real life example of how sometimes it can look a little bit messy if you've got things that are co-eluting and fragmenting together. However, you still can see, well, I've got all the fragments for MDMA, so I can isolate those. You can pretty much do almost like a deconvolution of taking the MDMA out of the interferon here. This is an example of what data dependent versus data independent, again, data looks like. You can see for, well, it's not the best view, but you can see on the right, you've got your 189 for, so this is fentanyl, 188, 337, you've got your 189, you've got your 338, you've got those M+1 isotopes. And then this is another example showing where you can have your M+2 isotopes. So when you're looking at the top spectrum, this data-dependent acquisition spectrum, because you're only isolating the precursor ion, you only get the fragments of that precursor ion. Therefore, you will not see the chlorine or bromine isotope pattern. And that's what's showing here. Again, you can kind of figure that out based on the accurate mass. You can see that the mass defect there, 0.99, that's going to be an indication likely that you've got a halogen there. You can see on the bottom of the data independent acquisition mode, it's very clear this compound is dually chlorinated here. This is actually, I think, U47700. So you can see this 172, and then you've got the M+2 at about 2/3 the height, this 174. So again, just some different ways the data looks. This is just to show that for our DDA method, we just have the drugs listed once in our library. For our DIA method, we have them listed 6 times, again, for the TOF-MS data. And then here under this fragment column, you can see we process and pull out the extracted ion chromatograms for some of the fragments. All right, so to conclude, what are some important things to understand? Well, first, you need to understand the difference between targeted and non-targeted in terms of analytical workflows. It's important to understand the differences between data-dependent acquisition and data-independent acquisition, especially if you're going to try and pick one. You need to understand what the two are. Hopefully, I've gone through some of that theory for you today pretty well for TOF and QTOF. Next, you need to understand that instruments, hardware, software, all of that vary by vendor. So you cannot expect to do on a SciEx QTOF what you can do on a Waters QTOF or what you can do on an Agilent QTOF. And at a high level, you can do the same things. You can inject a sample, get out a result, right? But all the in between is different. The way the quadrupole functions is different. The way the collision cell functions might be different. The software is certainly going to be different. So it's really important to understand. And really, when you get a QTOF platform into your or TOF or QTOF platform into your lab, you want to make sure you do as much research as you can to understand what your instrument can and can't do. Again, just because your QTOF can do it doesn't mean your neighbors can, and vice versa. And then I would just stress that there really is no right way to do TOF and QTOF acquisition. In fact, there are many, many right ways. It's highly dependent, again, on the purpose of your method, as I discussed. It's highly dependent on the set points of your method. Just because it's working or not working isn't because of the acquisition mode. It is much more because of those set points. And anyone that's worked on TOFs and QTOFs know that there aren't just 5 set points. There are sometimes hundreds of set points that you need to get right across all these different methods. And then you get into the Orbitraps and you get even more set points so you need to figure out. So just know that there's not a right way. Just because someone is doing it one way doesn't necessarily make it the right way. And then lastly, more and more forensic labs are using high resolution mass spectrometry. So now more than ever, it's a great time to reach out to colleagues for advice. There's so many people out there that can give you advice. If you're looking for advice on how to use a SciEx or a Waters platform, there are different working groups that have been put in place. So you've got resources out there, you've got friends out there that will be able to help you. Don't be shy about reaching out. So to wrap up, I do just want to thank my great team that I work with, specifically Josh DeBoard, for organizing this webinar. I'm very excited to hear the presentations of my colleagues throughout the day. And I definitely want to acknowledge the collaborators that we've had. We've worked very heavily and successfully with SciEx, Waters, and Agilent, and we appreciate all of their collaborations over the last several years. This is my contact information. If you're interested in more information, please feel free to reach out. Thank you for attending today. Thank you for listening, and I will be available for questions during the Q&A.
Thank you, Dr. Krotulski, for starting us off with that informative presentation. Up next, we will hear from Dr. Luke Rhoda with the San Francisco Office of the Chief Medical Examiner.
So good morning. My name is Luke Rhoda. I'm here to talk today about the development, implementation, and workflows and scope of QTOF analysis, specifically for the use in forensic toxicology and chemistry. And this is part of a course of our workshop today, sponsored and put on by NIJ, Forensic Technology Center of Excellence, and RTI. And so I thank them for the invitation today. Here's my disclaimer. So challenges relating to QTOF analysis as it relates to standards, validation, casework, resources, and of course, NPS and the continuing challenge with new drugs. So some of the challenges, firstly, relates to accreditation standards that we must meet and good quality assurance practices. So, for example, ISO 17025 is a requirement and standard that is universally accepted as the leading laboratory accreditation, and that dictates how we must do many of our workflows. There's also the specific and optional American Board of Forensic Toxicology, or ABFT, accreditation standard that many laboratories also meet around the United States. And there's a range of other variable parameters that should be met for good quality assurance programs in laboratories. There's also additionally recently added standards for the United States, but also been adopted more globally. And that were really kicked on and started off by the OSAC and now has been officially formalized as standards by the ASB. And they contain information about how to correctly identify drug analyses using your instrumentation. They provide minimum requirements for procedures, validation requirements, quality assurance programs, and also specific tests are relating to the different types of casework that you will actually perform in your laboratory. And then more recently, there's been a decrease in money and budget, typically also from the pandemic more recently. Human resources and just resources in general have been challenged. And that coincides, unfortunately, with an unprecedented overdose deaths, both probably at your local jurisdiction level, but also on a national level. And in addition to complex this even further, we have increasing novel psychoactive substances that have been more commonly detected over the years, but also further complex your forensic toxicology analyses as you have to add these drugs into your scope as they may become prevalent in your community. And so starting first with the American Board of Forensic Toxicology, or ABFT accreditation standard, one of the sections specifically mentions about written criteria requirements to identify a positive match, and it must include the acceptable retention time and mass deviation criteria. Another section includes, again, for identifying a positive match, it dictates that there must be a review of the underlying mass spectral data, and this has to confirm the general basis for the software match. And so you can't rely just purely on the software match, but there has to be some criteria and underlying analysis done by us to confirm a software match. There's also the ASB standard, and specifically ANSI ASB 98, the standard for mass spectral analysis in forensic toxicology. And this is a minimum standard for the practice for accepting MS data. Provides criteria requirements for acquiring data on a single or multiple stage MS, using either nominal LCMS or high resolution mass spec, such as TOF or QTOF. And it includes the range of ionization processes that we expect, namely electrospray ionization is probably the main one that we use in at least forensic toxicology and also in chemistry. And it provides some instructions for evaluating this data. And again, it can be used for different types of mass specs. And so specifically, one of the points that relates to TOF analysis is 4.4 that dictates single stage mass analysis criteria. And specifically that the spectrum shall contain the molecular ion at least. It also should have monitored diagnostic ions that should be within predefined mass errors and an isotopic distribution tolerance as demonstrated through method validation. I think the key word there is method validation. They don't dictate or set these criteria. You have to demonstrate that through your validation of that method. And we're monitoring more than one diagnostic ion. The ratios can either be of diagnostic ions can be assessed and should be within acceptable tolerances, or the spectrum itself should be compared using appropriate library searches and a predefined match factor, as demonstrated again through validation. The section relating to QTOF analysis, 4.5, is for that multi-stage QTOF type analysis. And again, this dictates that you should at least observe a single diagnostic product ion to be monitored, and that all monitored diagnostic ions should be, again, within the predefined mass error and isotopic distribution, again, by the criteria set at validation. It also says that you can either assess these diagnostic product ions by ratios, or again, by a predefined match factor using a library search, again, through validated criteria. Additionally, it also mentions that no ion should be present at a relative abundance equal to or greater than 50% of that base peak. And it should not be present in this reference spectrum. And you can use deconvolution software and background subtractions to assess this and mitigate this. However, it needs to be documented when used. And so here's some examples of some insufficient methods that do not meet the identification criteria. You may have an immunoassay with high resolution laser diode thermal desorption that only reaches a scoring of 3. You could also have a high res GCMS with only 1 ion, but that still only reaches 3.5. You can also have an immunoassay with other analyses that actually reaches 6.5 above the 4, but there's no chromatographic technique to actually help separation, and therefore it doesn't actually also pass this test. Briefly, some examples of over 4 are listed here. Specifically listed is the high resolution LCMS TOF with full scan spectral library matching, and that's a 4.5. You can also add immunoassay to this and bump that up. And you can also add high-res LCMS with 2 ions, and that would give you a score of 6. There's also other recommendations and also standards by ASB for the different types of casework. So, for example, in drug-facilitated crimes, or also known as drug-facilitated sexual assaults, there is both recommendations from SOFT, that is quite large and broad, and there was also a minimum standard by ASB that should also be met by people analysing these types of casework. Similarly, there's one for DUID, impaired drug driving, and a recommendation article really that has become the main go-to for looking to develop a method and also adhering to recommended guidelines. And there's also an ASB minimum standard again. And lastly, for post-mortem, there's just a minimum standard currently by ASB, but really there should be, in addition to your method, hundreds of potential drugs, recreational, therapeutic, or novel, that you may encounter and probably will encounter at some point for post-mortem investigations. Method validation is always key and has been for many decades now. And really the most recent version of this is the ASB 36. And I've highlighted here interferences and selectivity and limits of detection, because really I think they're the ones that are crucial for TOF and QTOF analysis, whether you're screening or confirming drugs using this technique. So what are some solution and workflows using high-res mass spec and TOF and QTOF? So firstly, you really want to plan an efficient testing regime that includes also efficient methodologies in that. And here's where quality and efficiency play a hand-in-hand role. The better quality you have, the more time you have to spend on efficiency, and the more efficient you are, the more time you have to spend on quality. And so looking at these two equally, I think really provides the best opportunity for your laboratory, success, really. So with this, some of the planning you might want to consider is, of course, multi-analyte methods. I mean, these QTOF and TOF instruments are designed for general unknown screening. And so to have a multi-analyte method is what you want to be looking and using these drugs, these instruments for. Extraction should be simplistic, rapid, automated if possible, uniform, and particularly non-selective, which I think is important for when using this QTOF, and I'll talk about that next slide. Consistent methods across the board would help. So if you have a QTOF with also LCMS methods, if you can combine the extractions or have similar type of mobile phases or reconstitution, that really helps with how your larger testing regime can fit into play. And so thinking not just about the method, but the testing regime and how all your different methods can work together in an efficient manner can be really helpful. Looking at automated data processing really cannot be understated. I think that particularly with high-resolution mass spectrometry data that QTOF and TOF brings, the amount of data can be overwhelming, and that's something that we always hear about, is how many terabytes of data this can generate. But importantly, the complexity of the data and trying to process that data by one analyst in a morning or afternoon is tough. And the only way you can really do that is by automation of the processing method, using either Excel, queries, Python, or even the instrument vendors' own software, if they allow for different levels of automation and data processing. Take advantage of that as much as possible, because more than ever, data processing is most important for TOF and QTOF analysis. With that, you also want to have your quality assurance program built into all steps as much as you can. And so, for example, having those mass spec identification criteria that we mentioned before built into the processing method and not manually reviewed by an analyst, that's going to save you time. So it's efficient, but it's also better quality, which again saves you time and allows you to dive back into quality. So there is this circular process that can happen if you really install all of these quality assurance programs throughout your processing and throughout your whole workflow, really. And try to have simplified reporting as much as possible. So fewer methods, if you can combine methods, that just saves a lot of work. And don't be scared that QTOF can serve not just as a screening method, but also confirmation and possibly even quantitation. And surely in 10 years' time, I think that it'll be mostly used, I won't say mostly, but even more used as a quantitation method than just going straight to LC triple quad, for example. So in general, high-resolution mass spectrometry, here's some theory, and I won't go too much into this because other speakers will talk more to this about this today. But it certainly can be accurate and precise in terms of the mass spectral data that you get. Robust and sensitive. We see that the new generations of QTOF and TOF are now increasing the sensitivity where they're actually comparable and practical for everyday use, using not just post-mortem work where you're expecting high concentrations of a drug in an overdose, but even DUIs and sexual assaults where you want to go as low as possible and find that needle in the haystack. There really is no limit to how low you can or should go in a sexual assault case. And QTOFs are about to really move into that direction as the main, the current instruments of QTOF are able to provide that sensitivity. Sample prep, I think it should be simple. I talked just before about having a general extraction method. I think that's important to not have an overly selective sample prep. Otherwise, it really wastes your high-res mass spec data that you get. So having a solid phase extraction that is very specific for a type of drug chemistry, or even more specific for a drug class, can kind of render the high-res mass spec instrument kind of pointless, and you might as well just move to nominal mass LCMS at that stage. So just have a think about what we're trying to achieve with QTOF and TOF analysis. There can be short analysis time, of course, and eventually I think it will become cost effective if we think of all these parameters in terms of efficiency and quality built into the method. It can be a cost effective venture over time. Just some typical acquisition data. I won't go too much into this, but you can have this here for review later. Some MS parameters regarding to spray voltage, inclusion energies, and identification criteria. You'll see that the standards previously mentioned never really discussed an actual number for mass error, but typically 5 ppm has been a bit of a benchmark, but certainly there's able to be, you can report data or drugs analysis above that 5 ppm should your analyte come in above 5 ppm, but you probably should have validated criteria to still demonstrate that's acceptable. Isotopic ratio difference has been seen from anywhere from less than 2.5 or less than 80%. Retention time error, that's usually set at around 2 to 3%, but sometimes up to 5. And library scores typically of 70. But again, these all have to be validated by your own in-house method. Okay, and so diving into now the acquisition options for high-res mass spec. And firstly, looking at data-dependent acquisition, where here MS/MS spectra is produced with minimal interference. So it's quite specific for a precursor ion. And if you can tell, that's because on the right-hand side here, we see an image where there's a threshold line that must be met by that precursor ion in order to trigger an MS/MS spectra being initiated. And so you are really specific for that precursor ion. It does have narrow precursor windows, as just mentioned. It's typically specific for that precursor. It has preset conditions, so that threshold line has to be met. And that may actually cause some inconsistency in repeatability. So if you can imagine an analyte that falls just above it on one analysis, but falls below that threshold line on the second, it's not going to trigger the MS/MS spectra to be produced on that second analysis if that precursor is just below that threshold. And so you risk potentially missing some ions, and really that means risk of missing drugs. Data-independent acquisition is independent of these preset conditions. So there is no precursor threshold that must be met. And therefore, all product ions are recorded and their mass spectra data is really combined, which can become problematic. Even though all ions are fragmented, this does introduce the risk of interferences, of course, in your MS/MS spectra and result in potentially poor spectra matches. However, if done with certain techniques, a data-independent acquisition example might be something called SWOF, and that's a sequential window acquisition of all theoretical fragment ions spectra. And what this really means is in the Q1, we have an alternating window that allows certain number or certain preset precursor ranges through that Q1 for then eventual product ion development. And this is followed by consecutive scans. And so, for example, your first scan might go from 100 to 140 as your range that you're allowing precursors through, and then a slight overlap of 139 to 154.5 in the second precursor window. And so this alternates several times throughout the second to then create a minimized interference with your product ions spectrum. It's just as a precursor ions are reduced just down to those windows, but it also allows that all of the eventual precursors do eventually come through, which then can minimize and reduce the risk of missing any drugs. But it does mean that you need to account for internal standards. And so what we end up doing was a customized SWOF window where, for example, tramadol is in window 7 and has, but in window 8 falls the tramadol D3. And that's because if tramadol and tramadol D3 were in the same window, the internal standard of tramadol D3 would interfere with the tramadol, authentic tramadol's MS/MS library spectra, because they have the same, or they have very similar mass spectra. So we have to separate those internal standards in different swath windows. But that can be achieved, and this has been achieved for us, and we're able to have a simple extraction method of 150 microliters of either blood or urine. There's a 400 microliter protein precipitation of cold acetonitrile, and this contains those internal standards. This is then vortex for 5 minutes, and then a size exclusion filtration step occurs that is not containing any chemistry, but just simply size exclusion. Again, so we can really exercise and take advantage of the TOF and QTOF's general unknown screening capabilities. A filtrate is then put into a clean autosampler, dried down and reconstituted in starting conditions. In this method, we're able to analyze 750 to about 1,000 components, ranging from a dozen or plus different drug categories on a routine basis. And so, again, these are a general unknown screen method, and it's not specific to just one type of drug class, or even basic or neutral or acidic drugs. And so you'll see here that there's also drugs here, or drug classes that have many acidic drugs also in their drug classes. So stepping now to processing methods, and we're covering a lot of issues here about validation and verification criteria, data processing, and we really want to talk about the method development process for QTOF assays, and it's not linear. All right, it's not a straightforward stepwise process. And so now going into some of the identification criteria, and these are some examples of what's worked, for our method, but you certainly have to validate this method according to your own observations. And so mass error, we chose an immediate acceptable number of 5, for example, but a marginal acceptance of less than 10. The error and retention time was less than 2.5, and again, this is a percentage. Difference in isotope ratio less than 5, and a library hit score of at least above 70. And one step is to always look at your library curation. And we should be doing this on a either quarterly or annual basis at least. And there can be different levels of confirmation to your testing based on the library and reference that you have. So for example, levels 1 and 2 here, you can see really provide a bit more stronger confidence that the minimum data requirements have been met. And particularly level 1 for us is where we curated our own in-house library using reference standards that we actually purchased and injected on our system. And that provides the most highest degree of confidence for reporting analytes. And then of course, there's even outsourced libraries that can be purchased by either vendors or other library created by other laboratories. And they provide a different range of levels of confidence in identification based on also the data, the criteria data that's able to be passed. And so for us, in-house library detection allows us to report quantitatively, but also qualitatively straight onto a forensic toxicology report. Whereas if just referencing an outsourced library detection analyte, we would report that more so as a presumptive test pending confirmation. And so that library curation, as mentioned, we have about 1,000 compounds or more now that have been added to our in-house library. And we're looking at the MPS Discoveries quarterly trends, UNODC's annual reports, and more often the annual reports they put out, and of course the DEA also, and any information you have to discover new drugs. And when those new drugs are discovered, we actually will look at purchasing that reference material and injecting it into our method. But we have to look if it's fit in our acquisition, and does it actually fit into our acquisition or not? And if no, it must be omitted. So some things just don't elute, for example, an LC QTOF. And then we run a selectivity test, and we'll go into this a bit more later, and if they're grouped or standards, or grouped or by themselves. And of course, you need to validate at least interferences, limit of detection, and some minimum qualitative validation standards. And decide if you're going to report it qualitative, or if you have a quantitative QTOF method, are you going to move it to quant? Part of our library curation involves this identification criteria, and we've got 7 categories that we use. And essentially, if 2 compounds or 2 or more compounds have the same mass, they are greater, but they have a greater than 2.2 minutes retention time delta. If they have unique fragmentation pattern, they're in category 1. If they don't, they're in category 2. Similarly, if the retention time is less than this 0.2, but between 0.1 and 0.2, and again has unique fragmentation pattern or not, they'll be 3 or 4. 5 or 6 is if the retention time again is even closer for those 2 or more components. And 7 contains, I should go back, sorry. And 5 or 6, here is when we can actually, will actually say that in group 6, if it has the same exact mass, the retention time is between 0 and 0.1 minutes, and there's no unique fragmentation pattern, then we have to really join those 2 analytes or more and make it a grouped reporting name. Whereas from group categories 1 to 5, we're still able to report an individual analyte. And then in group 7 contains several possibilities, but really essentially the group name, these analytes are conservatively reported as a group. So group 1 example here for we can see here. So clobazam here on the left with that orange box was highlighted was actually injected into the system, and the method identified clobazam correctly as the processing method. And in the bottom right here, you can see that clobazam was also detected by the library matching. So that's great. That's category 1. That's an excellent situation. However, when we also injected the clobazam, temazepam also popped up in the processing method. However, the unique fragmentation pattern allowed for clobazam to be identified correctly by the library match, and therefore we're able to keep this as a category 1 because we can still quickly identify this analyte as clobazam and not temazepam. When you inject these side by side, you can see here that yes, there is a retention time quite close, but there is still separation. And again, their library matches designate that one's clobazam and one is temazepam. And here's a situation where we selected the wrong component intentionally and showed that temazepam was selected. And again, showing that we have accurate identification. So a category 6 example might be where we have levomethoxsalen injected, but dextromethorphan actually is highlighted in the processing method here in the red box as being detected. And in the bottom red box, the library match also indicates dextro. And so here we have no ability to really separate the levo or the dextro. Although we do get accurate detection for levo when injected levo, it comes up positive. Because of that dextro positive hit, they would both be, and the library mass spec is very similar. We would jointly report this as dextro/levomethoxsalen. So these grouping studies for us, they result in 188 interferences and combined the 62 groups. And so I think it's important to just demonstrate here that although we're talking about high-res mass spec data, you're not going to be able to separate many isomers and many different types of components. And so it's important to do these these interference studies and selectivity studies, and know that you're going to report these as groups. And it's better to detect something and report it as a group rather than misidentify or not identify it at all. So some applicability studies that we've shown using the CAP, NOB over the last couple of years, proficiency tests. For this study, we were able to detect accurately alpha PHP, alpha PVP, and a range of different cannabinoid and designer drugs. On retrospect analysis, we didn't have those other components added to our library and added to our processing method. When we went back and got the reference standards, added them to our library and reran that acquisition data, because it's swath, it's data that is non-targeted, and so we can go back and interrogate that acquired data. We're able to identify all of the drugs in that proficiency test last year. And then for the novel opioids and benzos from last year also, mostly all of them we could detect on the first go around. The others, we went and got the reference material, injected it into our library and created that library, and were able then to positively identify all of them in subsequent analysis. So that's great news. And what's been nice to see now, the evolution of our methods in 2023, that same NOB challenged by CAP, we're able to identify all the compounds straight from the start and report them out. Some solutions I want to briefly go over. Automation, and I won't go too much into this, but please dig into this or look into this. I'm happy to have questions about this, or contact me directly about what you can do for quality assurance and improvement using automated processing. Here's some things you can look at to automate in your processing. We don't do any of this manually. It's all automated. I think it's really important. And so finally, reporting. In abundance of caution, I think that we report from our QTOF only when we've actually obtained the reference material ourselves and have it in the library spectra, and we have validated that method. Otherwise, everything's presumptive or goes on to confirmation testing. But it means that we can report directly from the TOF or QTOF-MS, and it's defensible in court. And I think it's a really important step, and I think that in 10 years' time, hopefully, that's where most laboratories will be, because the powerfulness of QTOF, and people will talk about this throughout the workshop today, is really immense. But getting it right with validation criteria, standards, and efficient workflows is critical. And eventually, you'll have a report that you can produce, which is the ideal step and what you want for the end of the day. So I want to thank my team here at the San Francisco Office of Chief Medical Examiner and the Forensic Laboratory team. They're an excellent team, and specifically also Maria Sarkissian, who's now recently a PhD candidate and has worked on this method a lot over the last several years. So happy to answer any questions at this time, and my email address is there should anyone wish to contact me directly about QTOF and how to utilize it to its full extent. So thank you.
Thank you, Dr. Rhoda. Now we will hear from Danny Mata with the Orange County Crime Laboratory.
Hello, and welcome to the recommendations for sample analysis in the implementation part of this QTOF series. My name is Danny Mata, and at the time of this recording, I am a senior forensic scientist at the Orange County Crime Lab in California. A few disclosures before we start is that I have received an honorarium for participating in this webinar. And if I do mention any vendor, they are not sponsoring this webinar. However, the opinions expressed in this presentation are those of mine and do not represent those of the Orange County Crime Lab. So a brief outline before I get started. I'm going to talk to you guys today about instrument maintenance. Then we're going to move on to sample preparation and some pros and cons of some different techniques. And then at the end, we're going to wrap up with understanding the workflow and how that changes or is different or similar to the workflow that you currently use in your laboratory. But starting with instrument maintenance, a high resolution mass spectrometer, any sort of instrument, is very similar to other instruments in a general sense. You will have an LC, or you could possibly have a GC on the front end, but you are going to need preventive maintenance, which is generally performed by the company which you purchased from or another outside vendor. There are labs that do go through training so that they can perform this preventive maintenance in-house, and they kind of balance the cost of training one or two of their analysts versus bringing someone in. You will have monthly and weekly maintenance that does need to be performed. Many of those procedures can be obtained from your manufacturer specific to your instrument, but they can cover how often you replace a mobile phase or your washes, how often you clean an electrode, or your curtain plate or cone. Then there will be prior to use maintenance. This is similar to using any sort of LC, other type of LC instrumentation, where you will be priming your pumps and possibly your injector, making sure your calibration solution is there and the required amount is there. And then you will have your as needed maintenance, which can include changing your column or cleaning your Q-jet or your Q0, or unclogging any sort of clogs or fixing any leaks. When we're talking about time, some of this maintenance will take. We'll start with first your preventive maintenance. Most labs do those once a year. However, you can do it more often, and this is really going to depend on how many samples you're running, how often you're running, what is your sample type, how clean does your extraction get those samples, which we'll talk about in a few slides. So that will happen once, maybe twice a year, more often if you do need it. Every time you do the preventive maintenance, your instrument is going to be down for 1 to 3 days, depending on whether or not it needs to be vented in order to complete the maintenance, and then have to be pumped down afterwards. Your monthly and weekly maintenance should only take about 1 to 2 hours, if that, at the beginning of the week or the beginning of the month. Generally, this means you're going to be remaking some mobile phases or some washes and cleaning down that curtain plate or cone of your instrument. Prior to use, I have on this slide less than 1 hour. I would really say it's probably more like 15 to 30 minutes. This is going to entail, similar to the other LC systems, like I've mentioned, purging or priming your mobile phases and your injector. It can include making a calibration solution if you're making that in-house. And then you will also have to equilibrate your instrument before you do your first injection. The as-needed time for changing, say, a guard column or changing your column itself, really that physical aspect of changing those columns is very quick. However, you are, especially if you're changing your actual column, going to need to reprime that column, do some injections, make sure your retention times are where they're at. So that time, even though I say less than 1 hour, could potentially end up being more, depending on how much time you need to put in to getting that column ready to use. You can do some deeper cleanings, such as I mentioned, cleaning the Q-jet or the Q0. These can take a couple hours up to a whole day because you do have to vent your instrument, then perform your cleaning, and then pump it back down so that it is ready to go. Again, depending on how fast this is with your instrument, you could be down for an entire day. As for fixing leaks or fixing clogs, this depends, again, how fast you can find where the clog or leak is. And generally, as long as you have the equipment in-house, you can change those pretty quickly. The last thing I want to talk about with maintenance is the cost. We all know these instruments on the front end cost quite a bit just to purchase them, but then you have this yearly cost of your service contract. The main thing in your service contract you're going to want is that preventive maintenance. And if you only have that, or like ours is that and repairs, at the time of this recording, you're going to probably be paying around $40,000 a year. If you decide to do more than one preventive maintenance a year, because say your instrument's getting dirty due to your sample prep or the number of samples you're running, that cost is of course going to increase. As I mentioned, you can add repair on this. You can also ask for a specific response time. Many companies provide a 24 or 48-hour response time. Say if you only have one instrument, or even if you have a lot and they're running 24/7. But this is going to cost you quite a bit more. It could be upwards to $20,000 more, depending on how many instruments you have. But you do want to make sure, if you are going to pay for this extra response time, does it mean whether or not they are just responding by calling you back or emailing you back, or if they will actually be on site working on to fix your instrument and get it back in service. A lot of times parts are not included, so you want to make sure what parts are included and what are not included. Many times on the LC side, any parts where the liquid touch is not included and you actually have to pay for those yourself, even though your maintenance contract, they will repair it. Software updates, they can be free or you have to pay for them, but even if they are free, if you have to troubleshoot at all, you may want to have a software service contract. Again, this can be another couple $1,000s. Calibration solutions, if you decide to purchase them from a company, can run about a couple $100s per bottle, but can generally last a couple of months. You can also make those in-house and see if that is more cost efficient. And then again, these instruments are running on nitrogen. So whether or not you're running on dewars and you have that weekly cost where you're having to buy a couple of dewars a week to keep your instrument up, or you have a nitrogen generator, in which case you probably have another service contract in which you will need to pay for. So moving on from this instrument maintenance to sample preparation, we're going to talk about this and different aspects and different pros and cons of sample preparation. I'm not really going to go into the chemistries of any of these, but more like the pros and cons of each one, and really how do they affect your maintenance that we just finished talking about. Currently, the most common matrix to evaluate in the US is either blood or urine on a high resolution mass spectrometer. But oral fluid is becoming more common. There are also methods out there for tissues, hair, nails, and meconium, but a lot of what I'm going to talk about would more focus on blood or urine samples. So the first one we're going to talk about is solid phase extraction. Some of the pros of solid phase extraction is that you can get a very clean extract, which minimizes suppression and enhancement and matrix interference on the instrument. This clean extract leads to less maintenance on the instrument, and it's also possible to easily automate solid phase extraction on various platforms. Now, that could entail having another service contract on these platforms, depending on how complicated they can be. There's also in these columns various chemistries where you can increase some specificity for certain drugs if you're trying to lower your limit of detection. However, some cons are the columns do cost, and you're using one for every sample you're extracting. If you do decide to automate, you have either way, you will have an apparatus cost here. And if you automate, that will be even more costly. Again, these methods generally use quite a bit of solvent. And with here, you also have to pay to get dispose of that solvent. It is generally a longer extraction time, but if you can automate, then your analysts can walk away and do something else while the extraction is being performed by your automation. And it can get a little too specific if you're looking for a way to screen a broad-based screen covering many classes of drugs, such as your opiates, your muscle relaxants, your benzodiazepines, phenethylamines. Sometimes you want something that is not as specific when it comes to the extraction. Moving on to liquid-liquid extraction, this is very similar to SPE as the pros and cons, as you can get that really clean extract, which reduces your suppression and enhancement and your matrix interferences on your instrument. Automation is possible. However, there's less opportunities to automate for liquid-liquid extraction, and they're generally a little more complicated than for solid phase extraction. There are various chemistries that you can do. You can change your pH, you can change the solvents you're using to try and lower the limit of detections or get certain drugs out that maybe you weren't seeing before. However, again, with those solvents and changing those pH, you have that solvent cost on the front end and also the waste disposal on the back end. You're generally using more consumables with test tubes and pipette tips. And it does happen to be a longer extraction, similar to solid phase extraction, which you could automate. There also does seem, at least we've seen at our laboratory, there can be quite a bit of variation between analysts with your limit of detections in methods like this because of how much hands-on the extraction itself is. And similar to SPE, it can be too specific for broad screens, and that's covering multiple classes of drugs. The quickest and least specific extraction is your protein precipitation. It is very quick, non-specific. You have minimal solvent costs. You're generally not using a lot. And oftentimes what you are using, you're drying down, so you don't really have to pay for that solvent waste disposal because it has all been evaporated off. However, with this fast extraction, you are really increasing your chances of ion suppression and enhancement and matrix effects because the samples are significantly more dirty when you inject them on the instrument. However, you do get, and with this, you will have more frequent instrument maintenance, troubleshooting. You will probably have to change your column more often. So even though it's a lot quicker on the front end, what you're doing to your instrument may cost you more over time. Some other sample preparation techniques that we're not going to go into each one specifically, but with any of these techniques, especially with protein precipitation, you could add a filtration cartridge or filtration tips at the end in order to clean up the sample a little more prior to injection. Of course, this does increase the cost of your extraction as you can only use each one of cartridge or tips per sample. You can also use dispersive pipette extraction tips. This does also increase your cost per sample, and it can start getting more specific, like liquid extraction or solid phase extraction, as the sorbent within the tips could be removing drugs that you want to inject on the instrument. Supported liquid extraction and quenchers are very similar to solid phase extraction with your cost and with how you can automate them. Supported liquid extraction can use significantly less solvent than solid phase extraction, which is a pro, but again, you're using one of these columns or techniques per sample. In my opinion, for a broad class screen, doing a protein precipitation with an additional cleanup step, either the filtration cartridges or filtration tips, will allow you to analyze a broad range of drugs without dirtying up your sample as much as not including that filtration part at the end of the protein precipitation. So moving from your sample prep to actually understanding the workflow and how this will impact your laboratory, I'm going to talk about the changes, the similarities and the changes to some of the techniques we have historically used in forensic toxicology. There is the immunoassay, which most, if not all labs have used some version of this to screen samples. It is a relatively easy technique. You're just sampling all the cases and some standards, diluting it with a buffer, which can also be automated, so your analyst doesn't actually have to do that. And then either doing it manually or automating it on various different platforms. And then the results are read and you get a simple positive or negative. The automation, you have a lot of platforms to choose from because many other sciences, such as your clinical, your pharmaceuticals, can also use immunoassays, and they have been around for a long time. There's a lot of literature out there on them, which can definitely help with the issue of false positives and false negatives that can come up, especially in the recent years with NPS compounds out there. The paperwork for writing up one of these runs is relatively quick, same with the technical review, as it's comparing to one or two standards, that positive or negative, and then going on to a confirmation test. An alkaline drug screen, which is another historical technique in forensic toxicology, is definitely a little more hands-on. You are doing an extraction, usually a liquid-liquid extraction or a solid phase extraction, and then that final extract is placed onto an instrument, generally for a long runtime to reduce the chance of coelution between compounds. The data processing is also significantly more time-consuming than, say, an immunoassay, but generally lets you know whether or not a specific drug was detected rather than a class of drugs, which is what immunoassay does. So with these two historical techniques in mind, we can move on to the high-resolution mass spectrometry. And the pre-injection is very similar to your alkaline drug screen. You're going to have some standards and some samples, and you're going to perform an extraction, either one of the ones I talked about or some other sort of extraction. However, the standards part can get a little complicated because you have a lot of options. If you're doing a high-resolution mass spectrometer method that has 300 different drugs in it, what standards are you running with every single run? Are you running multiple standards with the same drug at different concentrations? Are you running those drugs or some or all of the drugs at the limit of detection every single time? Only standards containing compounds that are present in the confirmation method, standards not present in the confirmation method, where your high-res method is going to be the one where you're reporting from without a supporting method. And any of these, what concentrations do you run? It can get really complicated, and you need to think about your workflow. It is not a reality actually for my lab to run all 320 compounds that we look for with every single run. However, we do run about 150. We follow the two that are highlighted in red. Those 150 compounds are present in our confirmation quantitation methods. And since we have stock solutions of those standards for those methods, we do dilute down to the LOD so that every single run we can verify that we can see those specific drugs at the LOD in which we have said our method is looking for. But many labs throughout the country do this very differently, and you really have to look at your workflow and what works best for you. Next, when you're going to the actual instrument, you're going to have your pre-run set up, which is similar to what we already talked about, this maintenance side, priming or purging all the lines in the injector, making sure all your pressures are right, starting that equilibration. Then you're going to have an injection list, and you have to think of what order you want to run all your standards and your samples. And I'm going to show you an example of this on the next slide. And then you do have a within run calibration. How often do you want to run a calibration? We do ours every 20 samples with a 10-minute injection time. We were recommended to run this every 4 to 6 hours, but it's really dependent on your method. We definitely ran it more often because the temperature within our laboratory can change throughout the day, and running 105 samples means it's going to be running for about 19 hours. So our sample of our run list, you can see what we do on the bottom is we run a wash, which is just our mobile phase, our initial mobile phase, extracted blood blank, which only has internal standards, and then we run 3 standards, and you can see how we set it up here, and then we run all of our samples. We don't run any standards at the end to verify the instrument, but this is definitely a practice that is common in a number of labs. We also have to, for each one of those standards and all of the 320 drugs in our method, say what is the concentration of that drug in that standard. And again, you can see this here, and all of this can easily be automated either through Excel or through your software. So you're not having to type all this information in every single time, and it can be imported in a couple of minutes. Now, the processing part is really where all the time comes in. You need to check, however you decided to run those standards, you need to check all of them. You can, again, do that through Excel or through your software and make it pretty quick. You need to review all your samples and decide on your acceptance criteria, which I'm not really going to talk about because somebody is going to spend a presentation talking about your acceptance criteria. But once you have that, you need to mark drugs detected, indeterminate, or not detected. Now you have to create a report, and you have to decide, is that report going to include all 300 plus drugs in your method? Is it only going to include the detected or indeterminate drugs only? How are you getting that information into LIMS? What information are you putting into LIMS? And again, that can be automated. And then your technical reviewer is going to have to go through, and you need a process that they are checking to review. So this processing is definitely more similar to your alkaline drug screen, in which it is more time consuming than an amino assay. However, you do get significantly more information and drug specific information from here than you would on your amino assay. So in summary, you do have increased maintenance costs based off our historical methods. The instrument itself is more expensive, the maintenance is going to be more expensive, and not just with cost with parts and service contracts, but also time to make sure your instrument is running properly for as long as you can. You do have increased analysis time, and that's front end and back end, prepping your samples to processing your samples from immunoassay, but not really from our historical alkaline drug screen. However, you do get that increased specificity from this method because you know what drugs are specifically there versus from immunoassay where it's class. This can also help you guide in future method development and validation, and kind of be a better tool to determine where you need to focus at rather than guessing if they're drugs you've never detected before in your laboratory. And that comes with that increased information you get from this method, which you can do by data mining previously analyzed cases, which I know somebody else is going to talk about. So again, I didn't focus on that. So there's definitely a lot of pluses to moving over to a high resolution mass spectrometer that in my mind outweigh the cost of the maintenance and just the learning time of processing and training someone on the new method. At this point for the live presentation, I will be sticking around for any questions, but I have also put my contact information here in case anybody wants to reach out after that time and has any questions for me. Thank you very much.
Thank you, Danny. We will now hear from our final presenter before the morning Q&A, Dr. Caitlin Palmquist with the Harris County Institute of Forensic Sciences.
Good morning, everyone, and thank you for the introduction. Again, my name is Caitlin Palmquist, and I am a toxicologist 1 with the Harris County Institute of Forensic Sciences in Houston, Texas. Today, my presentation will focus on method validation and verification on QTOF-MS platforms. Before we get started, I do have a few disclosures. First, I'm a paid employee of the Harris County Institute of Forensic Sciences. I have no conflicts of interest in the material of this presentation. These speakers have received honorarium for participating in this webinar, and the webinar is not sponsored by any of the instrument vendors mentioned in this presentation. So I've broken this presentation down into 2 different parts. The first part will be about method validation to include the importance of validation, establishing a validation plan, and meeting standard requirements for QTOF-based methods. The second part will address method verification and ensuring that QTOF-specific aspects are addressed in line with forensic toxicological analyses. This includes things like method performance, establishing acceptance criteria, defining method purpose or intent, and establishing an appropriate quality control program that meets your laboratory's goals. So before we dive into the specifics of method validation as it applies to TOF or QTOF techniques, I want to quickly address the importance of method validation. Method validation, as we all know, is performed to demonstrate the reliability of forensic testing. We as practitioners want to be confident in the results we are reporting to the community. The process of method validation acts as a documented record of performance, tests process robustness, and provides evidence that the developed method fits its intended purpose, all of which are important in performing high-risk forensic work. Method validation is also required by many accreditation bodies, therefore must be conducted. While there are many accreditation bodies that do govern forensic science practice, I will discuss standards published by the American National Standards Institute National Accreditation Board throughout this presentation. So the first step in the method validation process should be to establish a validation plan. As described in ANSI ASB Standard 036, validation plans should include the instrumental method, the sample preparation technique, the parameters or requirements to be addressed, and the experimental process associated with meeting those requirements. And this ultimately includes defining acceptance criteria. Now, high-resolution mass spectral screening techniques are unique. As described earlier in the webinar, HRMS instruments are capable of different data acquisition, leading you to gather a lot of information that can be processed in different ways. So it is difficult to fit these methodologies into one standard box. And to my knowledge, there are no finite validation guidelines specifically for HRMS toxicological methodologies. That said, of the method types that are described in ANSI ASB Standard 036, the requirements for qualitative confirmation / identification methods are most appropriate for our purposes. In the creation of your validation plan, acceptance criteria beyond that of baseline requirements may be difficult to define, and this is a concept I will discuss in depth later in the presentation. So here's an example of a validation plan that we wrote for phase 1 of our LC QTOF-MS screen at the Harris County Institute of Forensic Sciences. On this plan, we indicated the extraction procedure and the instrumentation that we plan to use, the matrices of interest, and a list of target compounds and internal standards that we intend to validate. Continuing on, we provide a detailed list of all of the proposed studies, which included characteristics to be evaluated, actions to be taken, samples to be tested, and acceptance criteria to evaluate the results. At our lab, this document is approved by the Director of Forensic Toxicology and a representative from our quality management team, and this is before the validation even begins. It's important to note here that there may be things written in your validation plan that may not work as expected. So any discrepancies from your validation plan should be addressed and documented in your validation summary, which comes way later in the process. It is beneficial to have a well-constructed validation plan because first and foremost, it will keep the process organized. QTOF validations can be very cumbersome and complex, especially if many drugs are included. The validation plan can serve as a guide for conducting experiments, making sure all requirements are met, and can serve as a quick reference while reviewing data. Some things to consider when developing your plan include your laboratory-specific requirements. For example, as previously mentioned, accreditation body requirements. Not all accreditation bodies provide the same standards or guidelines, and not all labs have the same governing body. Next, alignment with your existing SOPs. You want to create a process that cooperates with your lab's routine procedures. And lastly is meeting or expanding scope in line with the type of testing that occurs in your laboratory. So that could be anything from postmortem, human performance, etc. Another major factor you want to consider is when you will address or assess verification concepts. This includes things like quality measures and defining QTOF-specific acceptance criteria for reporting that will prove applicability of your method. The verification process can be done before or in conjunction with validation, and I will address this idea further later in the presentation. So first, I will discuss the different parameters required for a TOF or QTOF validation according to ANSI ASB Standard 036. And I'll provide a few examples going along with those parameters. But before that, I want to mention that there is a relationship between all of the described parameters in creating an optimal validated method. During validation, it's like a game of tug and war until balance is met, especially when considering additional aspects of QTOF utilization. And ultimately, you may not even realize that all of these things exist until you're knee-deep in validation. So the first requirement that I will go over is carryover. Carryover into subsequent samples is assessed by analyzing blank matrix after a high concentration sample or reference material. This process is performed in triplicate, and a method is considered to be free of carryover when no analyte is observed above this established limit of detection. Increasing concentrations can be assessed to determine the highest concentration at which the method is free of carryover, or upper limits of the method can also be assessed. If carryover is observed, the method should be modified, or the resulting SOP should describe how to handle these carryover situations. Depicted on the bottom of the slide is an example comparing the results from left to right of a high concentration sample, a sample at the selected LOD concentration, and a negative re-inject following the high concentration sample. In this example, it is easy to see that carryover does not occur. But for drugs more prone to exhibit carryover, determining LOD is a critical factor in determining the presence or absence of carryover. Next is interference. Interference assessments are broken down into 3 categories. The first involves endogenous interferences found in the matrix of interest. When possible, at least 10 different matrix sources should be analyzed. These samples are analyzed as reagent blanks and contain no internal standard. This process can be difficult depending on the number of drugs included in your method or the suppliers or providers of the sources of your matrix. Negative matrix, whether it's human or animal, can be expensive to purchase, and discardable de-identified case specimens, while they are readily available, may contain some of your compounds targeted in your method. The example on this slide is one discovery that we made during our validation. It is decanoyl L-carnitine, which is a fatty acid, and we found that it interfered with clonazepam, a prescription benzodiazepine. Both precursor masses are observed in the isotope spectrum. And when assessing the neat MS-MS spectra individually, you can see the contribution of both compounds to the sample peak. The second interference category is that of stable isotope internal standards. For this process, blank samples of each matrix type are fortified with internal standard only. The resulting sample is monitored for target analyte identifications. And conversely, the blank samples of each matrix type are also fortified with target drug and no internal standard, which are then monitored for internal standard identification. It is possible for reference materials to contain impurities of the D0 or deuterated component, so it's important to assess the contribution as to not interfere with detection limits. While not as substantial for QTOF analyses, it is also possible for drugs and/or internal standards to share fragment ions, which may impact observed ratios considered for identification. The third interference category is other commonly encountered analytes, which can include drugs of abuse, prescription medications, metabolites, and compounds structurally similar to the analyte or analytes of interest. With a QTOF drug screen, there are often many analytes of interest, which increases the number of compounds to test for interference. Interference samples should be fortified and extracted or prepared neat from certified reference materials at high therapeutic or lethal concentrations. 2 approaches for completing this validation requirement are running reference materials individually, which may take more time and resources, but would be finite in the identification of the interference. Or you can try running interference mixes, which may decrease analysis time, but if an interference is discovered, it may take more time to identify which drug from the mix caused the interference. Additionally, considering how drugs in mixes interact with each other may be beneficial for selecting your experimental process. Ionization suppression or enhancement by co-eluting substances is often encountered in LC-MS applications. Also known as matrix effects, the average suppression or enhancement value is considered to be acceptable within plus or minus 25%, or with a percent CV within plus or minus 20%. If a suppression or enhancement value is outside of that acceptable range, Standard 036 states that a laboratory must demonstrate no impact of matrix effects on critical validation parameters, such as LOD, which in the case of QTOF validation is the most appropriate critical parameter. That said, this is another situation where results of one parameter plays a role in another parameter, and then the process of performing the validation as a whole. Ion suppression or enhancement can be assessed in 2 different ways: post-column infusion or post-extraction addition. Both processes require the assessment of 2 concentrations, a low and a high, in 10 different matrix sources per matrix type. Limit of detection is an estimate of the lowest concentration of a drug in a sample that can be reliably detected and differentiated from noise. There are multiple ways to determine LOD, but all three methods require the analysis of three different sources of blank matrix across three analytical runs. Methods for determining LOD for QTOF experiments include establishing a decision point, which is also can be referred to as a cutoff concentration or an administrative decision point or cutoff. Determination by decreasing concentrations of reference materials, or estimation based on statistical analysis of the background. In the validation we recently performed, we utilized ASB scope standards to select decision points for relevant drugs. We then set up our experiment to bracket that decision point concentration and perform the laboratory work as described in the decreasing concentrations process. For any limit of detection process, all identification and qualitative acceptance criteria should be met, as mentioned earlier, is expanded beyond retention time, peak shape, and ion ratios when considering QTOF data. I'll dive more into QTOF specific criteria in a few slides. As we probably know, there are circumstances that sometimes occur far too often that prevent us from being able to perform analysis on a set of samples the same day they are extracted. Performing process sample stability experiments during validation will provide the laboratory with a window in which the target analytes remain suitable for analysis. For this process, blank matrix is fortified at low and high concentrations. The resulting sample extracts are divided into several autosampler vials and stored. Storage conditions often include refrigeration or on the autosampler at room temperature or cooled. Vial sets are then injected in triplicate at predetermined time intervals. These intervals are often daily, and data from each day are compared to T0 or that initial injection to assess the stability of the drug. Compounds are stable within acceptable bias determined by the laboratory, which my experience has often been 15 to 20%. When assessing high-resolution mass spectral data, there are additional aspects of the data that need to be considered and ultimately assessed as acceptance criteria. Many of these criteria are included in the processing methods on different QTOF platforms. These aspects include things like mass error, retention time, isotopic distribution, and library match score percentage. As of now, there are no standards providing finite HRMS screening acceptance criteria. So when performing validation, it can be difficult to know how to set such criteria. Just an example, the outlook that we took during our validation was to start with general acceptance criteria included as default within the manufacturer's software. Even these values can be adjusted to create wider ranges so that all possible results are captured. As a result, problematic compounds or issues with the method itself may surface. And many times within our validation data, we would print filtered and unfiltered reports for optimal evaluation of such criteria. Using our validation data, we can then start to narrow down acceptance criteria into more specific ranges that not only worked for our unique method, but also captured true positives and negatives, as well as reducing false positives and negatives. With the vast amount of data collected, we were also able to explore other means to support identification and or reporting through things like relative retention time, combination score, and internal standard recovery. While beneficial for our validation experience, this approach may be too extensive for the resources available at some laboratories, and a more conservative criteria from the start may be more appropriate. Due to the nature and uniqueness of QTOF screening, it is not without risk to establish criteria used in data processing. With that said, the complexity of these systems and ability to gather so much information about one sample may outweigh the risk, especially with the continued expansion of knowledge as it relates to the field of forensic toxicology. At some point before, during, or after the validation process, your method has to be verified for forensic toxicological applications. Existing and or new published standards should be considered, and I'll walk through a few of these on the following slides. You should refine the purpose of your method and understand how it will be used in the ordinary course of business at your laboratory. and a unique QTOF quality program should be developed and confirmed for implementation into casework. One way to test your quality program is to run a series of competency samples, such as previously analyzed proficiency or case samples. Many times, validation involves fortification of blank samples that may not necessarily reflect the true authentic specimen behavior. Assessment of authentic specimens can be the icing on your validation cake through demonstration of reproducibility and applicability of the method's intended use. To put this idea of verification into practical examples, let's say your laboratory has relevant pre-existing procedures, a defined application for the method, and a high level of experience with developing and using HRMS. It may be more suitable for outlining verification targets before validation and performing them in conjunction with validation. On the other hand, let's consider a laboratory with a brand new QTOF and no existing methods. The analysts developing may not have a firm purpose for the application or a firm definition on what they intend to use their method for. And this may require them to make adjustments throughout the validation process. Ultimately, verification can and will occur after the validation experiments have been completed in this case. There are many circumstances that will cause this process to be different for everyone. Nonetheless, monitoring method verification throughout development, validation, and into implementation will be beneficial. Just this year, ASB has published a few standards addressing identification. ANSI ASB Standard 113 specifically refers to identification criteria in forensic toxicology. At this time, these standards are voluntary for most laboratories in the United States, but I wanted to walk through them as they relate to QTOF-MS screening. For a brief background on Standard 113, identification is driven by a point system in which 4 points acquired from no more than 3 techniques are required for analyte identification. On this slide, I've included a screenshot from the document of the point values assigned to commonly used techniques. The standard lists some general requirements addressing the analysis of multiple matrices, the points per analyte, identification based on test specificity, and how to identify isomeric compounds. In addition, the standard states that at least one chromatographic technique, including a concurrently analyzed reference material, is required, and it continues to provide more specific details on scoring stationary phase per technique. As far as mass spectral requirements, the standard refers to an additional document that I will discuss on the next slide. That said, analysis by QTOF-MS with library matching has the ability to earn 4 points, which is the maximum number of points needed for identification in just one analysis. This is where the question of screening versus confirmation arises, as this instrumentation is capable of both. Not only that, routine forensic use necessitates following a defined protocol, whereas research-based use may not. It is important to clearly define your lab's intended use, as this will impact the validation process, implementation requirements, and testing scheme. ASB released standard 098 for mass spectral analysis in forensic toxicology. This standard addresses some of the acceptance criteria needed for high-resolution mass spectral analyses. And these criteria include monitoring one diagnostic product ion, defining mass error and isotopic distribution, comparing ion ratios or library searching with a predefined match threshold, and monitoring for extraneous ions. As you can see, the criteria described are quite vague, and ultimately discretion for acceptance is highly dependent upon method validation results. It is the ranges, thresholds, and values set at validation that has a driving factor in the accuracy and robustness of your method. While the standards provide overarching definitions, the specificity of acceptance criteria is vague. This puts a lot of power and flexibility into the hands of those performing development and validation, which can be overwhelming. The last standard I'm going to mention is ANSI ASB Standard 054, addressing quality control programs. To my knowledge, there are no finite rules for developing quality control programs for HRMS methods. Nonetheless, this document is full of useful information, and I will highlight a few topics that are relevant for QTOF-based quality programs. So the first is using certified reference materials when available, especially when you're creating an in-house library. Some labs will create library spectra of those reference materials at low and high concentrations to kind of cover a range of what they may expect. The second would be to strategically plan your quality control mixes. Your positive QC should challenge your LOD or cutoff concentration. You also want to consider maybe making several QC mixes containing different compounds, or making one representative mix, ensuring that you're still able to meet identification criteria for drugs within your scope. So for example, in our validation, we decided to prepare one QC solution with drugs representing different classes, as well as different retention times along our chromatographic gradient. We included drugs in the QC that we do not have a secondary confirmation method for, so that if one of those drugs is identified in a sample, we can repeat analysis of the sample using our LC-QTOF method, and it will meet guidelines for identification because ultimately it will be assessed against a contemporaneously analyzed reference material. The acceptance criteria that you use for positive controls will ultimately be the same as case samples, so you want to encompass the optimal criteria as previously discussed. Internal standards should also be assessed in a negative QC in every run, and internal standard recovery should be evaluated to assess the extraction of case samples. This is another consideration that may be tedious to determine due to not all target analytes having a matched deuterated internal standard. In the example of our method validation and process, we determined that internal standard recovery must be greater than 50% of that in the positive control, and that 9 out of 10 of our internal standards must meet acceptance criteria for the sample as a whole to be evaluated. Another thing you may want to consider in developing your program would be creating a procedure or system to monitor QC performance so that you can evaluate trends for how your QC behaves over a period of time. Just last year, Wiley et al. Published a review article analyzing 26 high-resolution mass spectral methods for qualitative systematic toxicological analyses that were published between 2011 and 2021. This article does a great job of summarizing how HRMS methods have evolved in recent years and the different aspects of HRMS methods, such as data acquisition types, available reference databases, and identification processes. In addition, the article addresses current guidelines being used for method validation of HRMS methods and highlights the need for more specific standardization with the increased demand of quality in forensic laboratories. The authors provide suggestions for method development, compound identification, and validation experiments. They also address important quality aspects, including measurement uncertainty. I highly recommend this read to those in all stages of HRMS development. So ultimately, there is no one-size-fits-all approach to validation of QTOF-based methodologies. As forensic science practitioners, we must perform method validations and verifications to ensure the reliability of our results. As discussed, there are limited documents available for addressing specific actions for bringing QTOF or HRMS methods online in a forensic setting. The ASB documents or standards listed on the slide can serve as helpful guides for this process, but as of now, ambiguity does reside in the language. While this may create a tedious development, validation, and implementation process, ultimately it does still allow for flexibility in the process for meeting your laboratory's specific needs. I wanted to end the presentation with a few tips and tricks that I learned from recently completing our QTOF validation. And first is to define a clear scope. This can include the compounds of interest, maybe broken down into tiers or how we did phases of importance or priority for your specific goals. This can also include how you plan to use your method and for what case types. Second is to consider acceptance criteria from the start. It can be overwhelming, but ultimately framing your criteria will help you narrow things down throughout the process. Third would be to perform experiments in smaller chunks. QTOF systems generate a lot of data, and assessing hundreds of compounds across multiple parameters can be overwhelming. And like my picture on the slide shows, it is a marathon, not a sprint. Lastly, and probably most importantly, is to reach out to other forensic toxicologists. Our field is full of awesome people who are always willing to share and help, and being able to pass along information, experiences, and what not to do's can make a huge difference in your validation experience. So with that, I want to thank you all for your attention. If you have any questions, please feel free to reach out to me or ask during the Q&A session. Thank you.
Thank you, Caitlin. I'm Joshua DeBoard. I'm a senior scientist at CFSRE. I will be monitoring our Q&A session today. Just as a note, Dr. Palmquist is also heading a QTOF workshop at SOFT in a few weeks. So if you're lucky enough to be registered for that, you'll be in for some more good information. And thanks also very much to Alex and Luke and Danny for contributing your knowledge this morning's session. And allow me to welcome our presenters from this morning as we begin our first Q&A session. I'll do my best to answer in a round robin fashion, but all of the presenters are welcome to jump in with your thoughts on any questions that are directed to another panelist as we go along. We'll start with the first question directed to Dr. Kotulski from CFSRE. The acquisition modes dictate, as you said, what data is produced, but a laboratory is, correct me if I'm wrong, not required to choose one of these modes at implementation. Or can other acquisition modes be used on that same instrument?
Sure, yeah. So the reality is that most labs will have several methods, several acquisition modes that they're using for a variety of different, essentially for a variety of different assays or workflows, whatever it may be. So yeah, so the lab is going to be limited by what acquisition modes they can use based on the platform and generally the manufacturer of that platform. So just because you buy a SciEx QTOF or an Agilent QTOF doesn't mean that you get kind of access to all these different acquisition modes. You are kind of stuck in whatever acquisition modes that platform and that manufacturer, that vendor offers. But then on the other side of that, you can have multiple methods. Like for our, at the CFSRE, we actually have both data dependent and data independent acquisition modes. We just so happen to use our data independent acquisition mode the most frequently and for our routine toxicology testing. But we have our data dependent acquisition mode, our IDA method, available for research, for metabolism work that we do, for addition of standards to our library database. So so you aren't necessarily stuck with just one acquisition mode when you're once you've got an instrument. You don't have to just pick one. You can still change between acquisition modes. However, once you go forward and pick an acquisition mode and validate that method, then you are stuck with that acquisition mode, if that all makes sense.
Yeah, thanks. Does anyone else have any input onto what generally the acquisition mode in use in your lab tends to be?
I was just going to agree with Alex that in statement, what we ended up choosing and validated, that's what we kind of stick with at our laboratory. We do have, say, the more non-targeted method that's not validated that we won't report from, that we kind of monitor stuff with. But our validated, we use IDA, we have a SciEx, would be the one that we stick with because that's what we validated through.
Yeah, and as you mentioned, Caitlin, validation is quite an arduous process. do you guys plan to have a research component to your methodology, or to strictly use validated methods?
I think as of now, we will be using it for just strictly for casework. But we do have plans to like continuously validate as more drugs come on the market. And we only validated one phase of 3 we have planned. So it's kind of going to be an ongoing process.
Nice.
Yeah, I think, Josh, just one final comment on that.
Sure.
I think one of the really interesting things to me over time has been to see what different types of acquisition modes labs are using, because like I said, at the end of my talk, there's really not one way to do this. So Luke and his lab in San Francisco have a SciX X500R. Danny in Orange County have a SciX X500R. Kayla Ellison, who I know is listening in Travis County, they have an X500R. We have an X500R, and all 4 of us are not using the same acquisition mode. We're not using the same method. We're not using the same library. So there is even a lot of variability in just the same labs that are using the same instrument, or different labs that are using the same instrument.
Yeah, that's a valuable point.
We also have an X500R.
Sorry, Caitlin, I did not mean to leave you off. I was just trying to go through my mental list of everyone.
Alex, to the idea, IDA and independent data analysis, are there differences with respect to how libraries can be searched on those different modes?
Yeah, I didn't have much time to get into this, just because the library searching itself can be quite complicated, and the algorithms and everything that go into it. So each vendor is going to have, I mean, they're going to use the same type of principles, but I think they actually do have different language. I know on the SciX instruments, there is three different types of library searching. There's fit, reverse fit, and then purity. So fit is saying, is the ion there in the data? Is it there in my spectrum? And do they match? Reverse fit is more concerned about what ions shouldn't be there. So are there ions in my data that are not in my library? And then purity is really the combination of the 3 of those. And that is a really oversimplified version. So just depending on how you acquire your data, you may have to use a different type of library search. So a lot of people using IDA and the data dependent acquisition modes use they usually use purity, because they do care about ions being there and not being there. With our swath methods, we can actually only use fit because we can get fragment ions of other drugs in the same fragment spectra as our drug of interest. So because if you're not sort of deconvolving those ions out, then you can get issues of poor library search quality, which really is related back to the acquisition mode and not necessarily the data. So yeah, there are different ways of comparing to libraries, and that's actually something that usually gets evaluated. I know we evaluated that during our validation to see which one, well, early on in our validation, obviously once we picked which one we were using, that was one that we used moving forward through the validation. But we actually tried to see which one worked best. Was fit, was reverse fit, or was purity the best for us?
And I know you kind of skimmed over the LC topic. I assume all of us are using LC to couple to our QTOFs and TOFs, but are you aware of any other capabilities or technologies that might be coupled to QTOF, and do they serve any purpose to forensics?
Sure. I mean, for sure there are. Yeah, I would say the overwhelming majority of us, probably 90-95+%, if not higher, are using LC TOF or LC QTOFs. GC QTOFs do exist though, and I know some labs out there do have GC QTOFs. But yeah, for the most part, the challenge is, and it really depends on the area. So GC QTOF actually probably works really well in forensic drug chemistry, even things like DART paired with QTOFs or other instruments, and different ways of getting your sample, introducing your sample into the QTOF. There's a lot of different options there. GC QTOF is difficult in the forensic world because you run into the issues of derivatization. One of the reasons why labs moved away from GCMS to LCMS was, in a lot of ways, to avoid derivatization, to increase sensitivity. So you can get better sensitivity with a GC QTOF, but you may not be able to get away from actually being able to see things well because they're underivatized. So, so there are other options. It's just that the LC pairing is by far the most common.
Yeah, and according to the ASB documents, it's that pairing to chromatography that gets you over the acceptance, criteria with those point scores. Let me direct a question to Caitlin, please. How long would you say the validation process for a QTOF could be? And let's say, understandably, it will take some time for someone's first validation versus, the experienced technician or scientist to do, but give a rough approximation for that if you can, please.
Yeah, so I would definitely say it depends on a couple of things. It depends on your lab's time, availability, and resources. Some people may not have the ability to work specifically on the QTOF validation process, whereas we were fortunate enough to have a method development team, so we were able to kind of devote all of our time to that. And even then, it still took us a few weeks to do all of the experimental bench work type things, and then several months to do all the data analysis, just because there's so much of it. And because the standards right now are so vague, we wanted to make sure that in our process, we kind of went through and met and checked every single box. But I know, again, for some labs that may not be practice. So it may not take that long. So it's so hard to like put a timeline on it because it really just depends on each individual lab circumstances. But I would say a couple of months to a year.
And how big is your team that's involved in that?
We had two main people working on it.
Okay.
And
Yeah,
Joshua,
and I'd imagine that your follow-up validation will be much more efficient, now that all of the one-time processes have been built out with respect to, your data handling and data analytics processes. So yeah, the first one is always kind of a doozy.
I would say,
Joshua, can I also add in? Oh, sorry, Danny, you go for it.
Oh, okay. Thanks, Luke. Sorry. So for ours, it actually took us 18 months from the time the QTOF came in-house. And the first 2 months, because we had a number of people that didn't even have LC experience, it was just like learning the instrument, the huge, like steep learning curve, if it's something you didn't have experience with. And then just kind of the development, we were doing a QTOF screen for about 300 drugs, like purchasing everything, making sure all your isomers separate, and then the validation test, once you get them set up, even if you have a lot of drugs, are actually pretty quick. But then we had a good 3-4 months on the back end of just paperwork and IT and like doing all that like back end stuff to actually put it online and train people. So ours was about 18 months, and then, but we did make a process to add drugs later on. So right now, if we have a new drug that comes out that we want to add and it be in our validated method, we can do that in under 2 weeks and get it added and validated. So per our accreditation, we're good to go. So we didn't include a lot of NPSs when we first validated, because in 18 months, what was important in the NPS world, at the beginning of our validation versus at the end was completely different, but we have this process to add. So I'll agree with Caitlin. We were definitely not under a year. We got a second one. That one we were able to verify within like 3 or 4 months once, because we knew what we were doing. But it definitely, that first one, the learning curve itself is pretty big. Sorry, Luke.
Yeah, I think Danny, I think we did a workshop in 2019 to directly address QTOF method development and validation because of these. I mean, it's a very complex challenge, and I think still 4 years later, it hasn't got necessarily that much easier. I think that also the validation is an ongoing live thing. I mean, just to Danny's point just then, I mean, when you have new analytes come in, you need to also validate them if you want to include them in your scope of testing. Starting off with a base validation, just qualitative, of course, is I think the way to go. And knowing that it might not be right the first time, and you may have to continue to tweak and develop the method, and might be the second validation where the method is finally set where you want it to be. And even before the first validation, I would encourage people to get samples that are maybe extracted with other methods in your lab and just run them through the QTOF or the TOF, so you can get an understanding about the data and about what will be required and what interferences you see, and how your method works. Because I think that hundreds and hundreds of samples later, you're still learning about how your method is running.
Yeah, that's a great point, Luke. And that is a question I really wanted to bring up later, but since we brought it up, I'd like to, I'll let Danny have the first crack at it since you brought it up. But what is your process like for adding new analytes to your validated methods?
So we have to get a standard, hopefully with a CRM, so we can create a library. So we just inject it at, I think we start around like 100 nanograms per milliliter, get a spectrum, get retention time, all that good stuff. And then we're doing our interference studies, matrix interference studies, ion suppression enhancement, stability, and LOD. LOD, we have like a couple different ways depending on the drug. If it's something with therapeutic information, we try and make sure we at least can see the therapeutic level, or we do a true LOD study, say with an NPS. But if we, like I said, we can get all the work, basically all the lab work done in a week, mainly because the stability holds us up if it's only 1 or 2 drugs, and then a week to get paperwork signed off and what we need in our LIMS system and our IT stuff to get done. And then we've also created a method just to validate to remove drugs too. We used to have certain drugs in our method, and we decided we didn't want them. What are things we have to check to actually remove a drug if we need to do anything? Again, just to cover ourselves accreditation wise.
Yeah, it's a constant back and forth. Whenever you do something, you need to go back and check other things and potentially readdress the method itself when something is revalidated.
Danny, can I ask? Yeah, Danny, can I ask, when you have a compound that isn't fully validated, do you still have the opportunity to report that, but specify that compound isn't under validation or ISO standard, or do you just leave it as presumptive and then confirm with another method?
So right now we have decided we won't report anything from our QTOF that isn't validated. I don't think that's strictly by our accreditation. That's just how our lab decided to handle things. We will report if we can see it on a different method, we will report it there. But for the most part, like I said, since we got our process pretty smoothed out, and with the retrospective data analysis that I know somebody else is going to talk about in the afternoon, once it's validated, we can go back and use that the retrospective data analysis to say, yes, it's there, and then a second test with it validated in the method to confirm it and report it out. And that's how
right, so I guess
we've decided to handle it, but I know there's lots of different ways.
Right, well, I think that was what I was leaning to. I think that last point of, you can go back to your original data, and there's no issue about reprocessing that and then reporting it out that way at a later date.
Yeah, we would do that at a later date. We just won't redo it before we had validated it.
All right, the next question I have is going to be coming to you, Luke, first, although I imagine everybody kind of has some thoughts on this, but we'll start with you. From your presentation, it seems that there's a number of ways you can achieve the criteria for identification from a LC-TOF as well as an LC-QTOF. And you obviously have an opinion on which is the most cost effective, but if you could elaborate on that, please.
Sure. And you mean identification criteria as with the ASB standard identification criteria, or just in general? Yeah.
To the point
yeah.
scale.
Yeah. So I think simply, not simply, but today we're talking about LC and QTOF-MS or even just TOF-MS. You can achieve those 4 points using a library match. And I talked about that earlier today. I think that is sufficient. I mean, there's certainly, you can add on then immunoassay, and but I feel like with the selectivity that you can get with high-res mass spec, it's sufficient to not really necessarily need the ELISA. But of course, you do need a second analysis, whether it's a second aliquot or another blood specimen or another urine specimen in the same case, to detect that same drug, or another completely analytical method, LC triple quad, to confirm it. So there's different ways to set just to achieve the identification criteria and achieve the confidence in reporting. We've kind of stuck with the approach of just using, either LC-MS or LC high-res mass spec, and really having a multi-analyte methods where, and not specifying just a drug class for an LC triple quad or a drug class on the high-res mass spec, but using sort of universal methods that are able to minimize the different types of methods that we have in the lab. So that's been the most cost-effective for us. But it does take a lot of work. It took investment of years and years of investment to build up those multi-analyte methods.
Right. So I guess to my point, there may be labs, we're not, we're here to inform on QTOF, not to preach on QTOF, but there may be labs out there for which this capability might not be the right option. So especially, for instance, one that's already pretty far along with LC triple quad technology is confirmatory. Perhaps the investment might not be right at this time, but does anyone have any thoughts as to, a lab circumstance that you might not recommend pursuing QTOF?
If you're just doing
don't
blood alcohol.
What's that?
I said if you're just doing blood alcohol.
Right.
I mean, I'm a big supporter of QTOF. It has won me over, but I will say, and I think Caitlin pointed this out, if you don't have the people to validate it and you're spending the money and you're going to have this really expensive paperweight for years, I would say, don't do it then. Wait until your lab has the capabilities to actually put it to use, because otherwise I think it's just going to be a frustration for the whole lab if that happens. But I think it's a big.
Yeah, I would agree, Danny. And I would add that it's, I think, hard also to jump straight from GC-MS to then LC QTOF. If your lab has at least experience with LC triple quad, at least they can have experience with knowing issues with LC columns, Mebel phases, and all on the front end. That kind of solves half the problem. So I think certainly you need the people who are experienced, but we'll have to learn somewhere. But if you can learn from a basis of LC triple quad, I think it's a little bit easier than jumping straight from GC-MS.
Yeah, that's probably more than half of the battle right there. So
Perhaps
if you already have LC triple quad experience, it's maybe not so much a leap. Yeah. Go ahead, Alex. Sorry.
I was going to say, to your question about labs that may not need QTOF, I mean, there are some labs, and not necessarily forensic toxicology labs, there are some practices of analytical toxicology where you are looking for a defined scope. And if that's the case, if you only care about testing for 10 drugs, 20 drugs, then QTOF is kind of overkill, because you're going to be acquiring data for a lot more things that maybe you do or don't care about. I won't speak for the entire soft NPS committee, but I think it's quite apparent that when you look at labs that are testing for NPS, the labs that are doing it well are doing it by QTOF because of the sort of evolving nature of the class. It doesn't mean that there aren't labs that are doing it really well by triple quad or by GC-MS, but QTOF really, in a world of evolving drugs and drug markets that are very dynamic, if your jurisdiction is seeing the influx of new drugs every week, every month, it really is. I mean, the QTOFs are really great for being able to keep up with that, because the methods don't have to be sort of built from the ground up again.
Right.
I'll add, Joshua, that even though I mentioned this in the talk, that the instruments are getting a lot more sensitive, the QTOFs, and are certainly pushing now towards triple quad sensitivity that we sort of expect and need in forensic toxicology. But for drug facilitated sexual assaults, where there's no defined limit on how low you want to go. There is recommendations by SOFT and also an ASB, but my theory is that you should really just try to push as low as you can go, because we often have survivors or victims who present at days or week or plus later, and if we're able to find something in that urine, that's an important part of the investigation. So however, the QTOF I don't think is as sensitive as a triple quad still, and so we will still run our triple quad method for all sexual assault cases that has comprehensive 200 analytes, because it doesn't get those very low concentrations that we want in the sexual assault. So sometimes there's still a big room for triple quad over QTOF, at least in parallel. I don't think we do one or the other, but in parallel to test them.
Okay. One last thing before I want to kind of move on to a topic of instrument vendors. I have one more question for Caitlin, and is if you could please just briefly describe or explain the difference between validation and method verification.
Yeah, so I would say method validation is more like the experimental process of establishing your method and making sure that it's fit for purpose. Verification is more on the second step in ensuring that your method meets real life application. So in terms of forensic toxicology, making sure that it works for the case samples that you intend to run on it. So like Luke said, running some old samples or previously extracted samples, making sure that you're not, missing anything that you need to see. Another thing would be your acceptance criteria, making sure that the acceptance criteria that you validated also fits your forensic samples. And that all kind of rolls into your quality program, just having a rounded out quality program to make sure that your method is doing what you intend it to do from more than just a technical standpoint.
Okay. And I mean, to some degree that could happen prior to validation in some respects, because you would want to test that method's fitness prior to pursuing what could be an 18-month validation.
Right. So like with our validation, I called it kind of like a work in progress. Like we learn something new every day. But now that our first phase is established, I think it'll be a lot easier moving forward because we will have those like verification type parameters already set in place.
Yeah. All right. Well, we have about 15 minutes left, so I want to move on to what, kind of some lessons learned from past experiences in dealing with instrument vendors. So one of the pesky issues with running a QTOF is typically, unless you are very fortunate, you don't have a lot of redundancy on your instrumentation, and so when your instrument goes down, downtime and dealing with vendor maintenance delays can be incredibly problematic, putting you behind on sample analysis, and running into stability issues and things like that. So what have been your solutions for dealing with vendors and trying to overcome delays in maintenance or instrument service?
So I'll say for us, it's not normally the vendor, it's our county purchasing and financial to get service contracts on time. So we deal with this. We try and learn during install whenever they're out. We try and learn as much as possible of what they're doing so that we can do it ourselves as possible, even not just your basic cleaning, but maybe your deeper cleaning that some labs may have them come out. We'll learn and we'll do it in-house. Treat your maintenance people from your companies really well, and they will treat you really well. They'll give us procedures. have a lot of spare parts on hand. So if something is down, you know, you have it there. Even if you can't fix it yourself, you just need to get someone, a body in to fix it. At least you're not waiting on a part because weather has gone bad and now you're waiting for shipping or something's back ordered. So we actually keep a lot of spare parts on hand too for stuff we can and cannot fix in-house. So that would be some of, I guess, my suggestions.
Yeah, from my personal experience, that was the case as well. Like we had a service contract and Waters was our instrument provider at the time. They were very open to training us on how to do, you know, front end and pretty complicated maintenance. They would just send us all the consumables because it's, you know, a cost for them as well to send a service person out. So if you're doing it, you know, that's cost effective for them as well. So, you know, pursuing that training from the vendor can be helpful in those circumstances.
Yeah, it also makes it easier to troubleshoot. Like maybe you can tell something is wrong. You may not know why it's wrong or what exactly happened, but you can at least get that first, it is wrong. And then hopefully with time and experience, get further into that process and be able to do more of the troubleshooting, again, without having to wait on someone. Even if you're paying for, say, 48 hours turnaround time, that's still 48 hours if that's your only instrument that you're down. So we use ours, you know, 3-4 days a week, so that would definitely hold us up some.
Yeah, and if you've got somebody who likes to get into the instruments, definitely nurture that on your staff because those people will be valuable.
I just wanted to add, I agree with everything all of y'all said. We've been having this very similar experience. We have SciEx, and they have a lot of resources, not only like when the vendor comes out themselves, but they have a lot of resources online, not just for troubleshooting and maintenance, but also kind of to wrap it back around with like the software and just using the QTOF in general, that have been really helpful for us, like training staff, training myself when I first learned how to use a SciEx. So that's a good thing to lean into as well as those vendor resources.
And have you found them to be pretty helpful with you know, assisting some of the automation of data and with the LIMS integration?
We have not done any of that type of stuff yet. So I cannot comment on that.
I say the LIMS integration, at least for, again, we have a SciEx, was pretty simple for us, but we also have a custom LIMS system that we made in-house. But I do know that can be a headache for a lot of labs, is that LIMS like transfer. But SciEx at least was very supportive and had a number of people we could reach out to work with that aspect of it.
And what kind of requests do you make when asking for that? Just application support generally, or LIMS assistance?
I mean, I generally go, I'm not shy, so I will email everyone I know at SciEx if I need help on something. But actually a really good start is your salesperson, because they really want you happy. They want you to buy more. So if you're looking for help on something that you not sure, it's not your hardware engineer that comes out to do the maintenance on your instrument, reaching out to your salesperson, they will almost always point you in the right direction of who to help and actually stay on top and make sure you're getting the answers that you want to keep you happy.
Joshua, one thing that is not really maintenance necessarily, but it is part of the vendor experience is the software. And honestly, I think that the software was probably lacking when QTOFs and TOFs first came out. The ability to process the data in a timely fashion and to utilize the wealth of information that high-res mass spec brings. I do think that the new generations are catching up. And then allowing automation and really thorough interrogation of the data within the software, or to allow the data to be exported and brought back in. So I believe that softwares of the vendors are improving. I think that we're working with our vendor to improve the software. And I think that's going to be the next big leap, I think, in QTOF, because the data is really great, but if you're running a few cases a day, it's not a big deal. But if you want to do, 100 cases a week, you need some kind of high throughput software that can automate things and lean on new programming and Excel and availability. So it's not really maintenance, but it's definitely something that I would talk with the vendor if you're talking with them about purchasing a new instrument. Is what are the software capabilities? How can you help us get set up to do some kind of timely processing?
Yeah, that's a very important thing to get on the front end of that discussion, for sure. I do actually have a couple of questions that I'd like to address from the chat. So we still have about 15 minutes to handle some of those. So we'll start with Alex for this question, because it is, I assume the DIA is in reference to data independent acquisition. But when validating a data independent acquisition method for DUID screening, how do you evaluate matrix effects? And Caitlin, feel free to chime in with this as well. Anyone as well too.
Sure. If you've seen me talk about our QTOF and the validation process, you'll probably know that I don't have all that positive opinions on matrix effects. I don't think there's a practical way to evaluate them, especially coming from a postmortem perspective. There is no way to upfront evaluate every type of postmortem sample you're ever going to get. It's just not possible. We get samples that are cloudy. We get samples that come from decomposition. It's really challenging. In the DUID space, it is a little bit different when you deal with antemortem blood, but that's not to say that, I mean, I'm sure everyone on here is, everyone listening has experienced one blood sample might be more thick and the other one might be more like water sometimes. And there's really no way of doing that well, I think. We do the best that we can. So for a data independent acquisition mode, I think the process of just making sure that you don't have any matrix interference is really important. So because with the DIA method, your method's not changing, you're not sort of adding things to it. I think you can have pretty good certainty in that if you run, maybe you need to run more than 10 blank matrices, right? Maybe if you run 10, 20, 30 plus and know that you don't have any issues there, that's certainly important. I think it's probably unrealistic if you're going to have a QTOF method that has hundreds and hundreds of drugs in it. I think it's probably unrealistic to evaluate matrix effects for every drug in multiple types of blood samples. So I think just getting an understanding of that could be a limitation of the method is probably important. Because it's a qualitative assay, you're not really going to be affected as much other than on that lower end of your LOD. So that's really where you have to start to come into, or start to think about kind of where those issues may arise. If you've got a sample that's 50 nanograms per mil and you've got 50% suppression, it's really not going to matter if your LOD is 0.5 nanograms per mil, right? I mean, that sample's still being reflected on for confirmation. So that's just a lot of words to say that there's probably not a practical way to do it. Certainly it's something that's important to assess, but it's not maybe as straightforward as anyone can really answer. But
well, what is your best practice then, Caitlin?
Yeah.
So the way we've done matrix effects in the past, or at least with our validation, is we put drugs into mixes, just because then you can assess a few drugs in those 10 sources at a time instead of having individual drugs in 10 sources times however many drugs you have. We've typically used post-extraction addition for the actual calculation of matrix effects. But like Alex said, the no blood is ever going to be the same. We've had purchased human blood that just, the matrix effects were so bad, it was like we couldn't even use any of the data. So we try to use multiple varieties of blood. So we'll try to use animal blood, human blood, like no tox bloods that have been de-identified and discarded. We'll try to use decomp just to try to capture a range of things that can happen. But again, once you do the calculation, you never know.
Okay. Yeah, it's a complicated question for sure. not one that has a straight answer. So we'll move on to our next question. And this is in regards to duplicated or mirrored methods across multiple instruments. So the person asking this question has the budget we all envy. So if you have 2 to 5 identical instruments, can you just copy validated methods from one instrument to the other, or is there enough of a difference to affect results between instruments?
I think robustness is the only criteria here. If you've got identical instruments, identical columns, mobile phases, everything identical, robustness really is, I think, the minimum that you need to do, which can be achieved in a few days. So,
Does it have that luxury?
So we have, I think Luke, you may have done this, but we have 2 SciEx QTOFs. Actually, one was an X500R, well, the new one was an X500R, old one was a 5600 plus. And we were able to mirror that instrument. So we were able to use the same chromatography, which allowed us to use the same retention time database. And then the library was the same because we were acquiring data in the same way on the mass spectrometer. So the fragment spectra were the same. And we were able to sort of almost copy paste and verify that process. However, I didn't know if that was going to work when we first started doing it. There was a lot of, as Caitlin talked before, about validation versus verification. We truly validated our 5600 plus method. We then, maybe you would consider it verified our X400R method, although we did the same process, so it really was a validation. But we verified though that everything worked, that the retention times really were still the same, that that the fragment spectra really did still work. So that would definitely be my recommendation. If you're able to get 2 or 3 or 4 QTOFs, having different methods is probably not ideal. Being able to mirror them all across the instruments makes everything in life so much easier, especially then when you can have you can kind of take the data from all the different instruments, force it through or process it through the same processing programs. Makes life a lot easier from a lab perspective. So it is possible.
Yeah, I would say we have 2. We were lucky enough to have 2. And when we got our second one, we just verified, we went through, were there any changes? And of course, everybody knows 2 exact same instruments, you still have differences between them. I can tell you our first one, our older one, is more sensitive, and we get better sensitivity on that than our newer one. But we didn't redo LOD in triplicate and all the different matrices. We maybe did it once and verified that LOD was still acceptable on the new instrument. And if there were differences, then we may, for like certain drugs, we would have maybe fully revalidated that specific drug, but we wouldn't have redone that for all, 300 drugs. And I'm with Alex, we called a verification. We did re-inject everything just to check retention times, even though like none of them, or they barely changed. I think that's just a comfort level because we don't inject standards for all 300 drugs every time we do a run. So we wanted to make sure the retention times for those that we don't check on a regular basis were still showing up where they should.
We got a few questions about LODs. Can anyone speak to what a typical LOD might be on a QTOF assay?
I mean, so it'll definitely be matrix and method dependent. The majority of our LODs, though, are sub nanogram per mil. But again, it's really going to depend on matrix. I think our
one of the questions specified blood, but
blood, yeah. Our blood, our fentanyl blood, yeah, I know still some of the drugs in there were fentanyl, morphine. So some of the drugs that are a bit more challenging, like morphine, are generally going to have slightly higher LODs. I think our LOD for fentanyl, though, is something like 0.2. I don't actually know off the top of my head, but it's pretty low. Morphine's a little bit higher. So then like BZE, our cutoff for BZE through a basic extraction is quite poor, obviously. Synthetic cannabinoids, though, for the parent drugs, we have really good sensitivity down, again, below 1 nanogram per mil. So I'd say for the most part, if I could like say for all drugs, it's probably somewhere on the 0.1 to 1 nanogram per mil range LODs for all the various drugs that we look at.
I would also just think that, you know, if you're buying a new QTOF, you could probably think of it as maybe a 3 or 4 year old triple quad. I feel like the QTOFs are a few years behind in sensitivity. And so if you've got a point of comparison of a triple quad, you can probably think about where it's going to land. But again, it's also method dependent. I mean, if you're targeting a certain drug class, then of course you can get better sensitivity, but really QTOFs and TOFs are designed for this general unknown screening. And you kind of get what you get when you do that. And so, but I think it's at this point now sufficient for certainly postmortem tox and DOIs, and hopefully in this next several years, sexual assault casework will it may be the only thing you need for sexual assault casework to reach those sensitivity.
Yeah, there was one question on the topic of using QTOF technology for drug identification. I did put an answer in the chat, but I'll bring it up anyway. Just the person asking was just polling if anyone does actually use it. And at CFSRE, we do confirm our drug identification by QTOF. It's especially helpful for NPS compounds, obviously, but does anyone else run any drug materials through their QTOF?
So our lab got one earlier this year for our drug section, and they're almost done validating it. So they will be running. It's been a big change for them, kind of similar to tox, where it was a big change for us, just because of how much they have to dilute the samples in order, from a GC to your LC QTOF. But we're really excited because we're hoping that'll really help us with what's in our county. So we'll focus more our toxicology work, which is why I'm excited, versus then, trying to sort through emails and references of what's coming around. Now we'll know directly from them what's in our county and hopefully be able to focus not just their validation and what they're looking for in the future, but also us in toxicology.
Yeah, that's great. I think there is generally a concern about instrument contamination from drug material, but the dilution factor that we use is about 1,000-fold or greater for those samples. So yeah, there's quite a bit of dilution involved to bring them down to the levels that a QTOF is not overloaded or contaminated.
Yeah, ours is 1,000-fold. From a GC, they dilute that 1,000-fold more for the QTOF, and we've been pretty good. California is your meth capital, I feel like, and so we do find meth everywhere. We had to play a lot with the LOD, or the signal to noise, and the acceptable response for our meth cases, so to try and combat some of that possible carryover. Same with cocaine, heroin, just because that's what they see a lot, and we don't want to miss those NPS or the fentanyl that's at lower amounts mixed with your heroin and your cocaine and your meth.
Yeah,
I think it's not so much also about your diluted auto sample vial, but your prepared vial, but also about where you do the preparation. I think you want to do your preparations in complete different locations to avoid that issue.
Good point, Luke. I think I have time for one more. And I think I'll go with this quantitation question as opposed to speaking. There was one about LC QTOF versus Orbitrap. I mean, honestly, I would say they kind of go hand in hand. Does anyone want to quickly volley why somebody might prefer QTOF over an Orbitrap, or they kind of just minor functionality differences?
I would agree. I mean, our lab evaluated, we did have a thermo Orbitrap at one point. I mean, you really need, in any scenario, you really need a dedicated scientist who's going to be able to understand the ins and outs of the technology one way or another. The benefit of a TOF is that all of the set points for the TOF analyzer are pretty much set. You don't mess around with the pusher. You don't mess around with the detector at all. The Orbitrap is not necessarily the same. There's a lot of things you can do and how ions are injected into the Orbitrap, how many times they cycle around the central rod, and then are injected. So the methods are a little bit more complex. But if you have someone who's dedicated to being able to understand that and put good time into evaluating those methods, obviously Thermo has a bunch of sort of boilerplate methods, if you will. But that's really the only difference. At the end of the day, they both work very similarly. Orbitraps inherently can be more sensitive than QTOFs. So that may be a benefit, but yeah, at the end of the day, they're pretty much the same.
Okay, thanks. One final question. Is anyone using their QTOF for quantitation, or is it strictly qualitative?
We have aspirations for quantitation, but it hasn't quite got there yet.
Yeah, I'd say we're qualitative, and if we have aspirations, I would say that's not in the next 10 years for us.
Okay, I saved that one for last because I expected that was going to be the general consensus from everyone on that. So thank you, presenters, for answering all of those questions, and taking the time out of your day for providing your expertise for us. And this
Thank you,
concludes
Josh.
our morning session. Thanks.